Hello and welcome to Space Historians. I'm truly glad you've joined me tonight. Ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our little blue world. Tonight, we're embarking on a slow and quiet journey, not racing through the stars, but gliding gently through the galaxy we call home, and then venturing even farther toward the enormous, humbling shapes that fill the cosmic deep. Right now, wherever you are listening from, you and I are situated somewhere inside a vast, glowing river of starlight called the Milky Way. We are surrounded by more stars than we could ever hope to count, each one a sun, many with worlds of their own. And yet, when we look at the grand map of the universe, our entire galaxy, this home we perceive as boundless, is merely a small patch of brightness in an ocean of darkness so vast it almost defies comprehension. Before we begin this long, slow voyage outward, I often wonder where you might be joining from. Is it quiet where you are? Perhaps the gentle hum of the city outside has faded, or maybe you're somewhere the only sound is the whisper of the night itself. Are your eyes closed, letting the day release its hold? Or are you picturing the shapes of galaxies as we drift among them? Wherever you find yourself, that stillness is where our story begins, not out among the distant nebulae, but right here, within your own quiet space. If you find these quiet journeys through time and space a comforting way to unwind, or perhaps even drift off to sleep, a simple like or subscribe helps this channel continue its steady orbit, reaching others who might also be looking for a moment of calm and wonder. Now, settle in. Let your breathing slow. Imagine looking up, far beyond the clouds and the thin, protective veil of our atmosphere. There, stretching across the infinite black, is the Milky Way. To our eyes, it's a faint, ethereal band of light, a sight our ancestors have gazed upon since the dawn of humanity. But through the lens of science, it resolves into a breathtaking spiral galaxy, a swirling city composed of hundreds of billions of suns. Tonight, we'll explore this home of ours, and then, gently, we'll compare it to the true giants of the cosmos, the galaxies so vast they challenge our very sense of scale. Let's travel together, slowly, peacefully, to the quiet side of cosmic comparison. It is easy, perhaps even natural, for us to feel that our home is the center of everything, not necessarily in a physical sense anymore. Science cured us of that illusion centuries ago, but in a conceptual sense. The world we know, the sky we see, the galaxy we inhabit, all feel, intuitively, like the main stage, the primary setting for the story of existence. The Milky Way, that faint, luminous river of starlight stretching across the darkest nights, feels vast beyond measure. Its scale seems to define the very limits of grandeur. When we learn the numbers, they only seem to confirm this feeling. Our galaxy, a swirling disk of light, spans roughly 100,000 light-years from one edge to the other. That single number is a barrier against easy comprehension. A light year, the distance light travels in a year, is already immense, about 9.5 trillion kilometers, or nearly 6 trillion miles. To imagine something 100,000 times larger than that requires a leap of imagination so vast that the mind tends to slip, replacing the number with a simpler, more manageable feeling. Enormous, boundless, perhaps even infinite. Within this structure reside somewhere between 100 and 400 billion stars, each one a sun, many likely orbited by planets, perhaps numbering in the trillions. Our own sun is just one among them, a single grain of light in a city built of light. The sheer population of stars, the sheer scale of the structure containing them, feels definitive. Surely, this must be one of the great wonders of the cosmos, a place of exceptional size and significance. This feeling, this assumption of grandeur, based on our internal perspective, is the starting point of our journey tonight. And the hook, the impossible beginning, is the quiet, humbling revelation that follows when we manage, through the patient gathering of light from distant corners of the universe, to step outside of that perspective. The impossible beginning is this: our galaxy, the Milky Way, for all its perceived vastness, for all its hundreds of billions of stars, is not a giant on the cosmic stage. It is not even particularly large. By the standards of the universe, our magnificent home is perfectly, undeniably, average. It is a middleweight, a standard model, a quiet town in a landscape filled with sprawling metropolises. This realization is the hook, because it forces a profound shift in our understanding of scale itself. If this structure that contains everything we have ever known or seen directly, is merely average, then what does large truly mean in the context of the cosmos? What are the true giants? And what does their existence tell us about our own place in the grand, unfolding story of structure formation? To grasp this comparison, we must first try to hold the scale of our own home, not just as a number, but as a place. Imagine trying to leave the Milky Way. Even if you could travel at the speed of light, the absolute, unbreakable speed limit of the universe, it would take you 100,000 years just to cross from one side of the disk to the other. Our current position is about 25,000 light-years out from the galactic center, nestled in a minor spiral arm called the Orion Spur. From here, looking inward towards the constellation Sagittarius, lies the galaxy's bright, dense core, shrouded in dust, but known to harbor a supermassive black hole about 4 million times the mass of our Sun. Looking outward, the stars thin out towards the galactic rim, and, looking up or down, perpendicular to the disk, the journey through stars is much shorter, only about 1,000 light-years thick in our neighborhood. This structure, this flattened disk with its swirling arms and central bulge, is turning. Our Sun, carrying the Earth with it, orbits the galactic center at about 220 kilometers per second, or nearly 500,000 miles per hour. Yet, the orbit is so vast that it takes roughly 230 million years to complete a single lap, a galactic year. Dinosaurs walked the Earth the last time we were in this part of the galaxy. This is the scale of home. 100,000 light-years across. Hundreds of billions of stars. Trillions of planets, perhaps. A slow, majestic rotation taking hundreds of millions of years. It feels complete. It feels self-contained. It feels like an entire universe unto itself. And yet, when astronomers turn their telescopes to the dark spaces between the stars of our own galaxy, they find more light. Faint, fuzzy patches, distant smudges that, upon closer inspection, resolve into other galaxies, entire island universes, separate from our own. The nearest major one, the Andromeda Galaxy, lies 2.5 million light-years away. Its light, visible even to the naked eye as a faint haze on a dark night, began its journey towards us long before modern humans existed. And Andromeda, our closest large neighbor, is slightly larger than the Milky Way, perhaps 220,000 light-years across, containing maybe 1 trillion stars. Already, just one step beyond our doorstep, we find a galaxy that modestly outshines our own. But Andromeda is still just a neighbor. Another spiral galaxy broadly similar to ours in form and scale. To find the true giants, the galaxies that embody the impossible scale suggested by our own galaxy's averageness, we must look farther. We must look towards the great clusters of galaxies, the cosmic cities where hundreds or even thousands of galaxies are bound together by their mutual gravity. These clusters are the places where galactic evolution proceeds most dramatically. Galaxies within them interact frequently, colliding and merging over billions of years. And at the heart of many of these dense clusters sits a different kind of beast altogether. The giant elliptical galaxy, often designated as the brightest cluster galaxy, BCG. These are the true heavyweights of the universe. Unlike the delicate, flat, spinning disks of spiral galaxies like the Milky Way, giant ellipticals are vast, smooth, nearly featureless spheres or ovals of starlight. They lack the dramatic spiral arms, the dark lanes of dust, the bright knots of ongoing star formation that characterize our home. Instead, they glow with the steady, often reddish light of trillions of older stars, moving not in orderly rotation, but in random, crisscrossing orbits, like a swarm of bees trapped within an immense gravitational field. These giants are thought to be the end products of galactic evolution, formed through the repeated merging of smaller galaxies over cosmic time. In the crowded centers of clusters, collisions are frequent. Each merger disrupts the ordered structure of spiral disks, randomizes stellar orbits, consumes or expels the gas needed for new star formation, and adds mass to the central behemoth. Over billions of years, this process builds galaxies of almost unimaginable scale. Consider IC 1101, located at the heart of the Abell 2029 galaxy cluster, about 1 billion light-years from Earth. It is often cited as one of the largest, perhaps the largest, known galaxy in the observable universe. Its visible light extends across a diameter of roughly 6 million light-years. Let that number sink in. 6 million light-years. That is 60 times the diameter of the Milky Way. If IC 1101 were placed where our galaxy is now, its edges would stretch far beyond the Andromeda galaxy, swallowing our entire local group of galaxies whole. Our home, Andromeda, and all their satellite dwarf galaxies would simply become part of its vast diffuse halo. The number of stars within IC 1101 is estimated to be around 100 trillion. That's roughly 250 to 1,000 times the number of stars in the Milky Way. It contains more stars than perhaps all the other galaxies in its cluster combined. Its luminosity is correspondingly immense, shining with the light of trillions of suns, yet its glow is spread over such a vast area that its surface brightness is relatively low, appearing as a soft, extended haze. This is the scale of a true galactic giant. It is not just quantitatively larger, it feels qualitatively different. It is less like an island universe, and more like a small continent of light, a structure whose boundaries blur into the surrounding cluster. Its outer halo, filled with stars stripped from consumed galaxies, and the faint intracluster light, likely extends for millions of light-years, merging seamlessly with the gravitational domain of the cluster itself. And IC 1101 is not unique. Many other galaxy clusters host similar behemoths at their centers. This is the impossible beginning. The hook is the dawning realization that the structure we call home, the galaxy that contains every star we can see with the naked eye, the birthplace of our sun, our planet, and ourselves, is utterly dwarfed by these cosmic titans. Our perception of vast was based on a sample size of 1. When placed against the full spectrum of galactic sizes, the Milky Way sits firmly, perhaps even humbly, in the middle ground. This doesn't diminish the beauty or significance of our galaxy. In fact, it may enhance it. As we explore further, we'll see that the Milky Way's averageness might be precisely what makes it special. Its balanced size, its ongoing star formation, its relatively calm environment within the local group. These might be the very characteristics that allowed the long, slow, uninterrupted evolution necessary for complex life to arise. The giants, formed through violent mergers and residing in chaotic cluster cores, might be less conducive havens. Our ordinariness, then, might be the source of our extraordinary fortune. But to appreciate that fortune, we must first confront the scale. we must accept the hook. We must let go of the intuitive feeling that our home represents the pinnacle of cosmic structure, and open our minds to a universe populated by cities of light so vast they make our Milky Way seem like a quiet village by comparison. This is the starting point for our drift tonight, acknowledging our place, not in isolation, but in relation to the true giants that anchor the cosmic landscape. Only then can we begin to understand the forces that shape galaxies, the processes that build such diversity, and the quiet elegance of the spiral we call home. Our journey tonight aims to compare our home galaxy, the Milky Way, to the true giants of the cosmos. But before we can truly appreciate the scale of those colossal structures, before we can feel the comparison in a way that resonates, we must first firmly establish our starting point. We must ground ourselves in the reality, the structure, and the feeling of the place where it all began for us. We need to understand the setting of our own existence, not just as a name on a cosmic map, but as a vast, intricate, and dynamic environment that we inhabit from deep within. When we speak of the Milky Way, we are not really talking about something we can ever truly see in its entirety, not directly. Unlike the photographs of distant galaxies captured by telescopes like Hubble or Webb, which show us spirals and ellipticals face on or edge on as complete objects floating in darkness, our view of our own galaxy is inherently limited, profoundly intimate, and ultimately incomplete. We are inside it. We are embedded deep within one of its spiral arms, looking out through layer upon layer of starlight, gas, and obscuring dust. Imagine living your entire life inside a sprawling, complex city, but only ever seeing it from street level. You would know your own neighborhood intimately. You could sense the overall structure, the long avenues where traffic flows like stars along spiral arms, the bustling, crowded downtown core, the quieter, sparser suburbs on the outskirts. You might even glimpse distant landmarks through gaps in the buildings, but you would never be able to step back far enough to see the whole city skyline all at once, to appreciate its full shape, its true extent, its place within the surrounding landscape. Our view of the Milky Way is precisely like that. Every direction we turn, our gaze pierces through thousands, even tens of thousands, of light years of stars, members of our own galactic family. The familiar constellations, the individual stars we name and recognize, are all relatively close neighbors within this vast structure. The faint milky band that arches across a truly dark night sky is the cumulative glow of billions of more distant stars, their light blending together, concentrated along the plane of the galaxy's disk. We are looking into the dense forest of our own city from within. Astronomers have spent centuries painstakingly piecing together the true shape and scale of this city, not from a single, perfect photograph, but through a mosaic of evidence, clues gathered across the entire spectrum of light, combined with the unerring logic of physics. The shape that solidifies is one of breathtaking elegance, yet subtle imperfection. Our galaxy is a barred spiral. It has a large, flattened disk of stars, gas, and dust, roughly 100,000 light-years across, perhaps more. This disk is not perfectly uniform. It is organized into graceful spiral arms, regions of slightly higher density where stars and gas tend to bunch together, triggering new waves of star formation. Most current models suggest the Milky Way has 4 major spiral arms: Perseus, Scutum, Centaurus, Norma, and Sagittarius Carina, along with smaller spurs or bridges that link them, like side streets branching off the main avenues. These arms are not rigid structures, fixed like the spokes of a wheel. They are more like dynamic patterns, density waves that propagate through the disk, constantly shifting, evolving, merging, and reforming over millions of years. At the heart of this spinning disk lies a dense, elongated structure known as the central bar, composed primarily of older, reddish stars. This bar acts like a funnel, channeling gas and stars from the inner parts of the disk towards the very center. And at that center, shrouded from our direct view by thick clouds of interstellar dust, resides Sagittarius A*, the galaxy's supermassive black hole. This invisible anchor, weighing in at about 4 million times the mass of our Sun, governs the orbits of the stars closest to the core. While immensely powerful, Sagittarius A times is currently relatively quiet. Unlike the ravenous quasars seen at the centers of some younger or more disturbed galaxies, surrounding the central bar is the galactic bulge, a thicker, roughly spherical or peanut-shaped region crowded with mostly older stars, glowing with a soft yellowish-red light. And enveloping the entire disk and bulge is the galactic halo, a vast, diffuse, roughly spherical cloud of very old stars, ancient globular clusters, and, most importantly, the overwhelming majority of the galaxy's mass in the form of invisible dark matter. This dark matter halo extends far beyond the visible edges of the galaxy, perhaps hundreds of thousands of light-years in radius, providing the invisible gravitational scaffolding that holds the entire structure together and dictates its rotation. Without it, the outer stars of the disk would be moving too fast for the visible mass to hold onto them. They would simply fly off into intergalactic space. This, then, is the setting. A barred spiral galaxy, vast on a human scale, composed of hundreds of billions of stars, rotating slowly in the dark, held together by the gravity of matter both seen and unseen. Our place within this structure is, in cosmic terms, rather unremarkable, perhaps even fortunate in its quietness. Our solar system resides within the thin disk, about 25 to 27,000 light-years out from the galactic center, roughly halfway between the core and the visible edge. We are currently located in a minor spiral arm, the Orion Spur, a relatively sparse region nestled between the more substantial Sagittarius and Perseus arms. This location is significant. We are far from the intense radiation and gravitational chaos of the galactic center. We are not currently passing through a dense major spiral arm, where encounters with giant molecular clouds or nearby supernovae might be more frequent. We inhabit a galactic suburb, a place of relative calm and stability that has perhaps persisted for much of the 4.5 billion years since our solar system formed. This quietude may have been a crucial factor in allowing the long, slow, uninterrupted evolution of complex life on Earth. Our galaxy, however, is not just a static structure. It is a dynamic, evolving system, constantly in motion, constantly recycling itself. As we orbit the galactic center, completing one lap every 230 million years or so, we move through different galactic environments. Furthermore, the Milky Way is not isolated. It is the dominant member of a small collection of gravitationally bound galaxies known as the Local Group. This group includes our large spiral neighbor, Andromeda, the smaller spiral Triangulum, and dozens of faint dwarf galaxies, many of which orbit the Milky Way and Andromeda like satellites. Our galaxy is constantly interacting with these smaller companions, slowly accreting them in a process of galactic cannibalism that helps it grow over cosmic time. And the entire Local Group is destined for a grand merger between the Milky Way and Andromeda billions of years in the future. So, this is the setting in detail. A large, actively star-forming barred spiral galaxy, constantly recycling matter, slowly consuming its smaller neighbors, and moving steadily through space as part of a small galactic group, itself destined for a grand merger in the distant future. Now, how does this structure, this home, compare to others in the vast cosmic landscape? As established in our hook, the overwhelming conclusion from decades of galactic surveys is that the Milky Way is remarkably average. Its size, around 100,000 light-years across the stellar disk, is typical for a large spiral. It is significantly larger than the numerous dwarf galaxies, but dwarfed by the giant ellipticals found at the hearts of clusters. Its luminosity, roughly equivalent to 10 to 20 billion suns, is also standard for its type. Its mass, estimated at 1 to 1.5 trillion solar masses including dark matter, places it comfortably in the middle range. Its star formation rate, creating a few new suns worth of stars each year, is typical for a healthy, mature spiral. Even its structure, a barred spiral with multiple arms, is a common morphology. There is a certain comfort in this ordinariness. It suggests our home is not a cosmic fluke, but a standard product of the universe's structure-building processes. It implies that the conditions found here, a stable disk, ongoing star formation, a location away from extreme environments, might be relatively common, potentially increasing the odds that similar settings for life exist elsewhere. Our galaxy's averageness doesn't make it insignificant. It makes it representative. This setting, this specific galaxy with its particular size, structure, and history, is where our story unfolds. It is the backdrop against which all human experience has played out, and it is the starting point from which we now look outward, seeking to comprehend the true scale of creation by comparing our familiar home to the almost unimaginable forms that lie beyond it. Understanding the Milky Way, in all its typicality, is the first essential step in appreciating the true meaning of giant. Our setting is established, grounded in the familiar spiral of the Milky Way, a structure vast beyond human reckoning, yet understood now to be merely average in the grand cosmic tapestry. We reside within its quiet suburbs, looking out through a forest of stars, aware that our home is just one city of light among potentially trillions scattered across an expanding universe. But this understanding, this map of reality we now hold, was not easily won. For centuries, our perceived universe ended at the faint, shimmering edges of that milky band across the night sky. How did we discover the truth? How did the spark ignite that revealed the true, staggering scale of existence? This is the story of that discovery, the pivotal moment when a persistent mystery, long debated but unresolved, finally yielded to observation, forever changing our place in the cosmos. It is the transition from the calm certainty of a contained universe to the thrilling, unsettling intrigue of an infinite one. The mystery lay in those faint, fuzzy patches of light scattered among the sharp points of stars, objects catalogued by astronomers for centuries, and simply labelled nebulae, or clouds. Some, when viewed through improving telescopes, resolved into glowing clouds of gas within our own galaxy. Stellar nurseries like the Orion Nebula, or the delicate, expanding shells of dying stars, planetary nebulae. Others revealed themselves as clusters of stars, still bound within the Milky Way's embrace. But many remained stubbornly nebulous, indistinct smudges, often displaying intriguing, enigmatic spiral shapes, unlike any known objects within our stellar neighborhood. What were these spiral nebulae? Were they truly internal gas clouds, perhaps solar systems in the process of formation, swirling disks of dust and gas relatively close by? Or were they something far grander, far more profound? As far back as the mid-18th century, the philosopher Immanuel Kant had speculated that these might be island universes, entire galaxies like our own Milky Way, composed of billions of stars, lying at immense distances, far beyond our galaxy's borders. It was a beautiful, expansive idea, but it remained just that speculation, a philosophical proposition lacking the anchor of empirical proof. The heart of the mystery, the barrier to resolving this debate, was the tyranny of distance. How could one possibly measure the distance to objects so faint and remote? Without a reliable cosmic yardstick, a standard candle whose true brightness was known, astronomers were lost in a fog of ambiguity. A faint object could be intrinsically dim and nearby, or intrinsically brilliant and incredibly far away. Its appearance alone offered no definitive clue. For decades, the question remained suspended, fueling intense debate within the astronomical community. The Great Debate of 1920, between astronomers Harlow Shapley arguing for the nebulae being internal, and Heber Curtis arguing for the island universe hypothesis, famously highlighted the passionate division and the lack of conclusive evidence. The spark that would eventually illuminate the path towards solving this mystery came not directly from studying the nebulae themselves, but from the patient, meticulous study of a peculiar type of star within our own galaxy and its nearby companions. These were the Cepheid variable stars, stars whose brightness rhythmically pulsates, growing brighter and dimmer over periods ranging from days to months. In the early 1900s, Henrietta Leavitt, working as a computer at the Harvard College Observatory, analyzing photographic plates of the Magellanic Clouds, nearby dwarf galaxies, made a discovery of monumental importance. She found a direct, precise relationship between the pulsation period of a Cepheid variable and its intrinsic luminosity, its true, absolute brightness. The longer the period of pulsation, the brighter the star actually was. This period luminosity relationship was the key, the cosmic Rosetta Stone astronomers had been searching for. It meant that Cepheid variables could serve as standard candles. If you could find a Cepheid in a distant nebula and measure its pulsation period, which is easy to do, just by observing its changing brightness over time, you could determine its true luminosity from Leavitt's law. Then, by comparing that known intrinsic brightness to how faint the star appeared from Earth, you could calculate its distance using the simple, fundamental inverse square law of light. Light fades predictably with the square of the distance. Suddenly, a reliable yardstick existed, capable, in principle, of measuring distances far beyond what parallax methods applied to nearby stars could achieve. The stage was set. The mystery of the nebulae lingered. The tool, the Cepheid standard candle, had been discovered. Now, what was needed was an instrument powerful enough to resolve these faint, pulsating stars within the fuzzy depths of the spiral nebulae, and an observer with the skill and persistence to find them. Enter Edwin Hubble. In the early 1920s, Hubble gained access to the newly completed 100-inch Hooker telescope at the Mount Wilson Observatory in California, then the largest and most powerful telescope in the world. Its immense light-gathering power offered the best chance yet to peer deep into the spiral nebulae and search for individual stars. Hubble decided to focus his investigation on the most prominent and arguably most beautiful of these objects, the Great Nebula in Andromeda, M31. His work was painstaking, demanding immense patience and meticulous attention to detail. Night after night, he exposed sensitive photographic plates to the faint light of Andromeda, capturing images over long periods. He then compared plates taken on different nights, searching for the telltale sign, stars whose brightness changed consistently over time. It was like searching for a single flickering candle within the combined glow of a distant city. In 1923, Hubble found his first candidate variable star in Andromeda. Over the following months, through careful observation and analysis, he confirmed it was indeed a Cepheid variable. He measured its pulsation period. He applied Henrietta Leavitt's period-luminosity relationship to determine its intrinsic brightness. And then, comparing that intrinsic brightness to its faint apparent magnitude recorded on his photographic plates, he performed the calculation that would change the course of human history. The number that emerged from his calculations was staggering, almost unbelievable. His initial estimates placed the Andromeda Nebula at a distance of roughly 900,000 light-years, while later refinements to the Cepheid calibration would push this value significantly farther to the currently accepted 2.5 million light-years. Even Hubble's initial, A conservative figure was revolutionary. The known extent of the Milky Way galaxy at the time was thought to be perhaps 100,000 light-years across. Andromeda, therefore, lay nearly 10 times farther away than the most distant stars of our own galaxy. The conclusion was inescapable, electrifying. Andromeda was not a cloud of gas within the Milky Way. It was not a nearby star cluster. It was, definitively, unequivocally, another galaxy entirely. An island universe, just as Kant had speculated, a colossal system of potentially billions of stars, comparable in scale and majesty to our own Milky Way, separated from us by an almost unimaginable gulf of intergalactic space. This was the discovery. This was the spark, the moment the old, comfortable, contained universe fractured, revealing an infinitely larger, more populated, and more mysterious reality beyond. The discovery wasn't just finding an object, it was the realization of a class of objects, the confirmation that our galaxy was not unique, but merely one instance of a universal phenomenon. The impact was immediate and profound. Hubble presented his findings in late 1924 and early 1925, effectively settling the great debate and launching the field of extragalactic astronomy. The faint smudges were no longer just nebulae. They were galaxies. The universe wasn't just the Milky Way. It was a cosmos filled with potentially billions of them. The calm, established boundaries of the known dissolved, replaced by the thrilling, daunting intrigue of the unknown, the unexplored, the newly revealed infinite. This discovery didn't solve all the mysteries, of course. In fact, it created many more. If Andromeda was another galaxy, what were the myriad other nebulae? Hubble and his colleagues turned their attention outward, applying the Cepheid method where possible, developing other distance indicators for farther systems, and confirming that galaxy after galaxy lay scattered across immense distances. How did these diverse structures form? Why did they come in different shapes, spirals, ellipticals, irregulars? Were they truly isolated islands, or were they connected in some larger pattern? The discovery that sparked the narrative wasn't an endpoint, it was the opening of a door. It transformed the central question of astronomy from mapping the stars within our home to mapping the archipelago of galaxies across the cosmic ocean. It ignited the investigation into galactic evolution, into the large-scale structure of the universe, into the origins, traced back towards the Big Bang itself. It provided the essential first step, the foundational realization of scale, upon which all subsequent comparisons, including our comparison tonight of the Milky Way to the cosmic giants, would be built. Hubble's identification of Cepheids in Andromeda was the key that unlocked the true scale of the cosmos. It was a moment where patient observation, combined with a crucial theoretical tool, Leavitt's law, resolved a long-standing mystery and, in doing so, gifted humanity with a universe far grander, far older, and far more filled with possibility than anyone had dared to imagine. The calm certainty of isolation gave way to the profound intrigue of abundance. The investigation into our place among the galaxies had truly begun. Edwin Hubble's discovery, announced quietly through scientific papers in 1924 and 1925, was more than just a measurement. It was a cosmic earthquake, a fundamental shift in the very foundations of reality as humanity understood it. The realization that the Andromeda Nebula, that faint smudge of light in the night sky, was not a nearby cloud but a separate colossal galaxy, an island universe lying millions of light-years beyond the confines of our own Milky Way, didn't just expand the known universe, it shattered the old one completely. The first human response to this revelation, rippling outward from the astronomical community to the broader culture, was, understandably, one of profound shock, followed quickly by a dizzying, almost vertiginous sense of awe, mixed with deep intellectual disorientation. Imagine, as we reflected before, living your entire life, believing your city, perhaps vast and sprawling in your perception, was the entire world. Then, one day, you climb a high mountain, peer through a newly invented spyglass, and see, stretching out to the horizon in every direction, countless other cities. Some similar in size and shape, some vastly larger, some strangely different, each teeming with its own unknown inhabitants, separated by immense, previously unimagined distances. This was the scale of the paradigm shift Hubble delivered. The universe, which had felt comfortably contained, knowable, perhaps even finite, within the familiar star fields of the Milky Way, suddenly exploded outward. It became unimaginably vast, ancient beyond reckoning, and populated by potentially billions, even trillions, of other galactic islands. The immediate scientific response was a scramble, a period of intense intellectual ferment. First came the need to verify. Hubble's meticulous measurements of Cepheid variables in Andromeda, grounded in Henrietta Leavitt's well-established period luminosity relationship, provided the crucial, undeniable evidence. Colleagues checked his calculations, observed Andromeda themselves with powerful telescopes, and confirmed his findings. Once validated, the long-standing great debate whether the spiral nebulae were internal gas clouds or external galaxies was decisively, irrevocably settled. The island universe hypothesis, once a fringe speculation, became the accepted reality. Our galaxy, the Milky Way, suffered an immediate and profound demotion. It was no longer the entirety of creation. It was just one member, perhaps an ordinary one, within a vast, newly revealed cosmic archipelago. This sudden, dramatic expansion demanded a new framework, a new language, a new way of organizing this bewildering zoo of newly recognized cosmic citizens. The first intellectual response, driven by the human need to impose order on chaos, was to classify. Edwin Hubble himself, having opened the floodgates, provided the initial, enduring structure. Faced with photographic plates revealing galaxies of myriad shapes and sizes, smooth ovals, elegant spirals, chaotic tangles, Hubble sought patterns. In the 1920s and 30s, he developed his famous tuning fork diagram, a classification scheme based purely on visual morphology, on what the galaxies looked like. It was a simple, elegant, and practical first step. At the base of the tuning fork handle, he placed the elliptical galaxies. These appeared as smooth, largely featureless ovals or spheres of light, seemingly devoid of gas, dust, or active star formation. He arranged them based on their apparent flatness, from nearly circular E0 to highly elongated E7. Branching off from the handle were the spiral galaxies. These were clearly distinct, possessing flattened, rotating disks characterized by bright central bulges and graceful arms winding outwards. Hubble further subdivided the spirals based on the tightness of their arms and the size of their central bulge. So galaxies had large bulges and tightly wound arms, while Skis and later Steed galaxies had small bulges and loose, often clumpy, open arms, rich in the blue light of young stars and the dark lanes of interstellar dust. He also recognized a significant subset of spirals possessing a prominent, elongated bar structure running through their centers, from which the spiral arms emerged. These he classified as barred spirals, SBB, SBC, paralleling the unbarred types. Between the ellipticals and the spirals, Hubble placed an intermediate class, the lenticular galaxies, S0, which possessed disks and bulges like spirals but lacked visible arms. Finally, any galaxy that didn't fit neatly into these categories, chaotic, distorted, or asymmetrical shapes, was simply grouped together as an irregular galaxy. Hubble's classification scheme was purely descriptive, a visual taxonomy, but it provided the essential first framework, a shared language for astronomers to begin discussing, comparing, and making sense of these newfound objects. The very act of naming and sorting spiral, elliptical, irregular was a fundamental human response, an attempt to grasp, to categorize, to impose intellectual order on the staggering, unexpected diversity of the extragalactic realm revealed by the initial discovery. It turned a sky full of confusing smudges into a catalogue of distinct forms. Alongside this intellectual ordering came the unavoidable emotional and philosophical response. A profound sense of scale shock. The distances Hubble and others were measuring weren't just large, they were almost beyond human intuition. Millions of light years. This wasn't just a slightly bigger backyard. It felt like discovering entire new continents, oceans, a whole world beyond the one village you knew. Light, the fastest thing in existence, took millions of years to cross the gulf between these galactic islands. The dawning realization that the light seen from Andromeda tonight had begun its journey when humanity's ancestors were first learning to walk upright was deeply humbling. This existential recalibration, this quiet but complete Copernican demotion on a galactic scale, was perhaps the most significant first response. Not only was our galaxy not the entire universe, but the universe itself was ancient beyond imagining, filled with structures comparable to, or even vastly larger than, our own home. The comfortable centrality, the intuitive sense of being in a special, privileged place, evaporated. Humanity found itself, intellectually and emotionally, adrift in an ocean of unimaginable size and age, populated by countless other islands of light, each potentially with its own history, its own stars, its own worlds, all mingled with a sense of profound smallness. Adding another layer of complexity and wonder to this first response was the growing significance of Vestos Slipher's earlier, enigmatic measurements of galactic redshifts. Slipher had painstakingly measured the spectra of dozens of spiral nebulae and found, surprisingly, that the vast majority showed spectral lines shifted towards the red end of the spectrum. This indicated they were moving away from us, many at astonishing speeds, hundreds or even thousands of kilometers per second. At the time, without knowing their true distances or nature, the meaning of this systematic recession was unclear, but once Hubble established the immense distances to these objects, confirming they were separate galaxies, the redshifts took on a revolutionary new implication. Hubble himself, driven by this connection, combined his new distance measurements primarily using Cepheids, but also other indicators for more distant galaxies, with existing and new redshift data. In 1929, he announced his findings. A clear, linear relationship existed between a galaxy's distance and its recessional velocity. The farther away a galaxy is, the faster it appears to be moving away from us. This systematic pattern, observed consistently in all directions, became known as Hubble's law. This discovery was the empirical proof of something even more profound than the existence of other galaxies. The entire universe is expanding. The galaxies weren't just static islands adrift in an infinite, unchanging void. They were participants in a dynamic, evolving cosmos. They weren't necessarily flying through space away from us due to some explosion. Rather, the very fabric of space-time between the galaxies was stretching, carrying them apart like dots painted on the surface of an inflating balloon. An observer on any galaxy would see all other distant galaxies receding from them in the same manner. There was no center to this expansion. It was happening everywhere. This discovery of cosmic expansion compounded the initial shock of discovering other galaxies. Not only was the universe vast and populated beyond imagining, it was also growing. The quiet, eternal, unchanging heavens, assumed by philosophers and scientists for millennia, were replaced by a dynamic, evolving reality, a universe with a history, presumably originating from some smaller, denser state in the distant past. The first response to this was again one of disbelief among some, but quickly followed by the dawning realization that the universe itself had a biography. A beginning, what would later be formalized as the Big Bang, and was subject to large-scale physical laws that governed its overall evolution over cosmic time. The scientific community's response, once the combined evidence for extragalactic distances and cosmic expansion became undeniable, was nothing short of a fundamental paradigm shift. The field of extragalactic astronomy was born overnight. A whole new, almost limitless realm of inquiry opened up. Telescopes were turned outward with renewed purpose, no longer focused solely on the stars and structures within our Milky Way, but on mapping this vast and newly revealed territory of galaxies stretching across space and back through time. The primary response became one of intense exploration, mapping, and attempting to understand the origins and evolution of these fundamental building blocks of the cosmos. This spurred an immediate technological response, the drive to build ever larger telescopes. If galaxies were truly millions and billions of light-years away, their light would be incredibly faint. To gather enough photons to study their shapes, measure their spectra, and search for standard candles within them required bigger mirrors, more sensitive detectors, and longer exposure times. The quest to understand the large-scale universe became a primary driver for pushing the boundaries of astronomical instrumentation, a legacy that continues to this day with giant ground-based telescopes and sophisticated space observatories. The theoretical response was equally dramatic. Physicists like Albert Einstein, whose general theory of relativity provided the mathematical framework for understanding gravity and spacetime on cosmic scales, had initially been uncomfortable with the idea of a dynamic universe. He had even introduced a fudge factor, the cosmological constant, into his equations to force a static solution, believing the universe must be eternal and unchanging. When confronted with Hubble's observational evidence for expansion, Einstein reportedly abandoned the constant, calling it his biggest blunder. The observation of an expanding universe became a cornerstone of modern cosmology, validating theoretical models like those developed earlier by Georges Lemaitre and Alexander Friedman based on relativity, that predicted such behavior, and leading directly to the development of the Big Bang theory as the standard model of cosmic origins. The first response among theorists was to embrace this dynamic reality and begin working out its detailed implications. Culturally, the response unfolded more slowly but was equally profound. The image of the universe shifted irreversibly. Gone was the single, perhaps divinely centered, Milky Way. In its place arose a picture of potentially infinite space filled with countless galaxies similar to our own, all participating in a grand outward expansion from a shared origin. This new cosmic narrative filtered into popular consciousness through science fiction, which eagerly embraced the concept of travel between galaxies, through popular science writing that attempted to convey the staggering scales involved, and through changes in education. It fostered a complex mixture of wonder and humility, wonder at the sheer scale, age, and richness of creation revealed by science, humility at recognizing our own planet, our own galaxy, our own species, as a small part of this immense, impersonal, and evolving system. The discovery resonated with ongoing philosophical and theological discussions about humanity's place and significance in a universe that no longer seemed designed around us. The first response to the discovery that sparked our comparison was therefore multifaceted and transformative. It encompassed the initial shock and awe at realizing our galaxy wasn't alone. It included the intellectual drive to classify and impose order on the newfound diversity of galactic forms. It involved the profound emotional and philosophical recalibration required by the revelation of unimaginable scales and cosmic expansion. It launched a new era of scientific investigation, focused on mapping the extragalactic universe and understanding its history. It spurred technological innovation in pursuit of fainter light from more distant epochs, and it slowly, deeply reshaped our collective human understanding of reality itself, situating us within a dynamic, evolving cosmos of breathtaking scope and humbling grandeur. The journey had just begun, but the landscape had changed forever. Edwin Hubble's revelations had irrevocably expanded the boundaries of the known universe, transforming faint nebulae from local curiosities into vast distant galaxies, island universes comparable to our own Milky Way. The initial human response was one of awe, recalibration, and an immediate drive to classify, to impose order on this newly unveiled cosmic zoo. Hubble's tuning fork diagram, sorting galaxies into ellipticals, spirals, barred and unbarred, and irregulars based on their visual morphology, provided the first essential framework. It gave astronomers a language to describe the inhabitants of this expanded reality. But very quickly, this act of classification, this attempt to impose scientific order, itself gave rise to a profound contradiction, a deep and enduring mystery. The universe, it turned out, wasn't just larger than we had thought. It was significantly stranger, more diverse, and governed by processes that didn't neatly fit the simple, elegant expectations derived from physics as understood at the time. The contradiction lay in the sheer variety itself, and in the dawning realization that the patterns Hubble observed hinted at complex histories and unseen forces we were only beginning to glimpse. Science, having just achieved a monumental victory in mapping the cosmos, immediately found itself confronting new, deeper levels of the unknown. The first layer of this contradiction emerged directly from Hubble's own classification scheme. The tuning fork diagram, with its smooth visual progression from round ellipticals designated E0 through increasingly flattened ellipticals designated E7, to the point where the sequence branched into the elegant arms of spirals, designated SAR, SPI, C, looked tantalizingly like an evolutionary sequence. It seemed almost natural, almost intuitive, to assume, as Hubble himself initially speculated, that perhaps galaxies evolved along this sequence over cosmic time. Maybe they started their lives as simple, amorphous elliptical structures and, as they aged, gradually flattened into disks, developed spiral arms through rotation, and matured into complex forms like the Milky Way. Perhaps spirals were the old age of galaxies, and ellipticals their youthful precursors. This initial interpretation, however appealing in its simplicity, quickly collided headlong with contradictory evidence gleaned from analyzing the light coming from these different galaxy types, specifically the information encoded within their stellar populations. When astronomers began using spectroscopy to dissect the light from ellipticals and spirals, breaking it down into its constituent colors and revealing the chemical fingerprints and ages of the stars within, they found a trend that pointed in the exact opposite direction. Elliptical galaxies, those smooth, seemingly simple structures at the base of Hubble's tuning fork, were found to be overwhelmingly dominated by old, cool, reddish stars, often billions of years older than the dominant populations in spirals. Furthermore, ellipticals contained very little cold interstellar gas or dust, the essential raw materials needed to form new stars. Consequently, almost no active star formation was observed within them. They appeared to be ancient systems, composed primarily of stars that had formed very early in the universe's history, after which the star-building process had effectively shut down. They looked like quiet, retired galaxies, their active, creative days long past. Spiral galaxies, in stark contrast, presented a picture of ongoing vitality, Their disks, particularly along the prominent spiral arms, were rich in vast clouds of cold gas and dust. Nestled within these clouds were regions blazing with the intense blue light of young, massive hot stars, indicating that star formation was not just a past event, but an active, continuous process. While spirals also contained older stars, particularly in their central bulges and halos, their overall character was one of youthfulness, activity, and ongoing evolution. Irregular galaxies often showed the most intense bursts of star formation, their chaotic shapes illuminated by clusters of newborn stars. Here was the profound contradiction laid bare. The galaxies that looked visually simplest and perhaps earliest in Hubble's morphological sequence, the ellipticals, were actually composed of the oldest stars and appeared to be the most evolved, or at least the least active, in terms of current creation. Conversely, the galaxies that looked most complex and structured, the spirals, were the ones still actively building new stars, appearing dynamically younger or at least more vital in their ongoing processes. The elegant tuning fork diagram wasn't an evolutionary path in the simple sense Hubble might have first hoped. The visual morphology told one story about shape, while the stellar content told a conflicting story about age and activity. Science had met a fundamental mystery. What, then, did determine a galaxy's shape? If not simple aging along the tuning fork, what physical processes sculpted these vast structures into such distinct forms and dictated their star-forming histories? This initial puzzle immediately led to the second, deeper contradiction: the mystery of galaxy formation and evolution itself. If galaxies didn't simply evolve along the Hubble sequence, how did these immense structures, spirals with their delicate disks, ellipticals with their ancient swarms, irregulars with their chaotic forms, come to be in the first place? The prevailing cosmological model, grounded in the Big Bang, described a universe that began in a nearly smooth, incredibly hot, dense state, and subsequently expanded and cooled over billions of years. Tiny, almost infinitesimal quantum fluctuations present in that initial state, variations in density from place to place, were thought to be the seeds of all future structure, amplified by the relentless pull of gravity over cosmic time. But how, exactly, did those minuscule primordial ripples grow into structures as massive and complex as galaxies? And, crucially, why did this process result in such dramatically different kinds of galaxies? Two major theoretical frameworks emerged in the mid-20th century to explain this, creating intellectual division and driving decades of observational and theoretical research. One model, often referred to as the monolithic collapse or top-down scenario, proposed that galaxies formed relatively quickly and early in the universe's history, from the rapid gravitational collapse of enormous, single clouds of primordial gas, perhaps millions of light-years across. In this view, the final shape of the galaxy was largely determined by the initial conditions of the collapsing cloud. A cloud possessing significant initial angular momentum, or spin, would naturally flatten into a rotating disk as it collapsed, conserving that spin, eventually forming a spiral galaxy. Star formation within this disk might proceed relatively slowly over billions of years. Conversely, a cloud with low initial spin, or one where star formation occurred very rapidly and efficiently during the initial collapse phase, consuming most of the gas before a stable disk could fully form, would result in a more spherical or ellipsoidal distribution of stars, an elliptical galaxy. This theory offered an elegant explanation for why ellipticals contained mostly old stars. They formed quickly and early, and why spirals retained gas and continued forming stars in their disks. Formation was slower, sustained by the rotating structure. However, the monolithic collapse model faced significant challenges as observational capabilities improved. Deep observations of the distant, early universe didn't reveal clear evidence of these predicted enormous, smoothly collapsing proto-galactic clouds. Instead, the early universe appeared populated by smaller, clumpy, irregular-looking structures, suggesting a messier formation process. Furthermore, the smooth, extended halos of old stars surrounding spiral galaxies like our own, along with their complex internal structures, proved difficult to explain solely through a single, rapid collapse event. The simple top-down picture seemed insufficient. This led to the ascendance of the competing theoretical framework, hierarchical formation, or the bottom-up scenario. This model, strongly supported by the predictions of cold dark matter cosmology, which suggested that small dark matter halos should form first and then merge, painted a very different picture of cosmic structure formation. It proposed that structure builds progressively, starting small and growing over time through a continuous process of gravitational merging. In this view, the first gravitationally bound objects to form were relatively small clumps of dark matter and primordial gas, perhaps only thousands or millions of times the mass of the Sun. These small clumps then merged to form larger structures, the first dwarf galaxies. These dwarf galaxies subsequently interacted gravitationally, orbited each other, collided, and merged over billions of years to build up larger and larger systems, spirals, and eventually giant ellipticals. In the hierarchical picture, a galaxy's final morphology is not predetermined at birth, but is largely sculpted by its merger history and its environment. Spiral galaxies like the Milky Way are thought to represent systems that have experienced a relatively quiet merger history, perhaps absorbing many small dwarf galaxies over time, but crucially avoiding major collisions with other large galaxies of comparable size. This relative peace allows their delicate, rotating disks of gas and stars to survive and sustain ongoing star formation. Giant elliptical galaxies, conversely, are seen as the end products of numerous, often violent, merger events, particularly the collision and coalescence of two or more large spiral galaxies. Such major mergers are expected to destroy the ordered disks, randomize the orbits of stars through intense gravitational scattering, trigger powerful bursts of star formation, starbursts, that rapidly consume most of the available interstellar gas and ultimately lead to the formation of a large, smooth, gas-poor, red and dead elliptical remnant. Irregular galaxies, in this framework, might represent systems currently undergoing mergers, galaxies significantly disrupted by recent gravitational interactions, or perhaps simply young galaxies still in the early chaotic stages of assembly. This hierarchical model seemed to better explain several key observations: the observed clumpiness and prevalence of small galaxies in the early universe, the existence of stellar streams and disrupted dwarf galaxies in the halos of large galaxies like the Milky Way and Andromeda, clear fossil evidence of past mergers, and the strong correlation between galaxy type and environment. With giant ellipticals overwhelmingly found in the dense centers of galaxy clusters, where mergers are expected to be most frequent, while spirals dominate quieter regions. The intellectual drama here arose from the fundamental shift in perspective. Galactic structure was not primarily set at birth, but was dynamically shaped over cosmic time by interactions, mergers, and the influence of the surrounding cosmic web. Galaxies were not static entities, but evolving ecosystems. However, even as the hierarchical model gained favor, it presented its own set of contradictions and mysteries, forcing further theoretical divisions and refinements. Early cosmological simulations based on the standard cold dark matter model, for instance, have consistently predicted far more small satellite dwarf galaxies orbiting large galaxies like the Milky Way than are actually observed, a discrepancy known as the missing satellites problem. Were the simulations wrong about dark matter? Or did they lack some crucial piece of gastrophysics that prevented stars from forming efficiently in these small halos? Furthermore, These simulations initially struggled to form realistic spiral galaxies with thin, stable, star-forming disks like ours. Simulated mergers often seem too efficient at destroying disks and creating bulge-dominated or elliptical systems. These tensions fueled ongoing debate. Was the basic cold dark matter paradigm incomplete, perhaps requiring warmer or self-interacting dark matter? Or did the simulations simply need to incorporate more complex and realistic models of gas cooling, star formation, and feedback processes like the energy injected back into the gas by supernovae or active galactic nuclei that could regulate galaxy growth and preserve disks? Minds divided, pushing both particle physicists and astrophysicists to refine their respective theories. Adding yet another layer to the contradiction was the profound mystery hinted at by Fritz Zwicky's early observations of galaxy clusters and later confirmed with undeniable clarity by Vera Rubin's pioneering studies of spiral galaxy rotation curves in the 1970s. The overwhelming problem of dark matter. Rubin and her colleagues meticulously measured the orbital speeds of stars and gas clouds at various distances from the centers of spiral galaxies, including our neighbor Andromeda. According to Newtonian gravity and the distribution of visible matter, stars and gas that astronomers could actually see, objects farther out from the galactic center should orbit more slowly than objects closer in, following Kepler's laws, much like planets in our solar system. But Rubin and her team found something completely contradictory, something utterly baffling. The stars and gas clouds in the outer regions of spiral galaxies were orbiting just as fast, or even slightly faster, than those nearer the center. Their rotation curves, plotting orbital speed versus distance, were unexpectedly flat instead of declining at large radii. This observation made no sense based on the visible matter alone. The gravitational pull exerted by the stars and gas clouds astronomers could account for was simply insufficient to hold those rapidly moving outer stars in orbit. The galaxies should be flying apart. The inescapable conclusion, profoundly unsettling yet demanded by the data, was that the vast majority of the mass responsible for this gravity, perhaps 80 to 90% of the total mass in these galaxies, was completely invisible. It did not emit, absorb, or reflect light at any observable wavelength. Yet its gravitational influence was overwhelmingly dominant, extending far beyond the visible edges of the galaxies in vast, roughly spherical halos. This unseen, unknown substance was given a simple, descriptive name: dark matter. This discovery presented a monumental contradiction, a deep chasm between what science saw through telescopes and what gravity required according to well-established physical laws. What was this dark matter? Its existence was inferred purely, yet powerfully, from its gravitational effects on visible matter. But its fundamental nature remained, and largely still remains, a complete mystery. Was it composed of exotic new, subatomic particles, perhaps relics from the very first second after the Big Bang, particles that interact with normal matter only through gravity and possibly the weak nuclear force? Was it something even stranger, perhaps requiring modifications to Einstein's theory of gravity itself on galactic scales, though such modifications face significant challenges? This profound mystery permeated every aspect of understanding galaxies, including their size, formation, evolution, and comparison. If most of a galaxy's mass is invisible and resides in an extended dark matter halo, then simply measuring its starlight or visible size gives a very incomplete and potentially misleading picture of its true scale and gravitational influence. Comparing the average Milky Way to a giant elliptical like IC11, O1 became not just a comparison of their visible stellar components, but more fundamentally, a comparison of the immense, underlying dark matter halos within which they are embedded. structures whose properties and extent could only be inferred indirectly through their gravitational effects. The contradiction was stark. The universe seemed to be built upon and governed largely by a substance we couldn't see and didn't fundamentally understand. Science had discovered its own profound ignorance, hidden within the elegant, predictable dance of stars obeying gravity's laws. The mystery wasn't just in the patterns, but in the stage itself. The universe, laid bare by Hubble's discoveries, was not only vaster and more populated than ever conceived, but also deeply puzzling. The initial, elegant classification of galaxies into ellipticals, spirals, and irregulars, intended to bring order, instead revealed profound contradictions. The visually simple ellipticals turned out to be ancient and quiescent, filled with old stars, while the complex spirals pulsed with ongoing starbirth, suggesting conflicting evolutionary paths. Underlying this was the pervasive enigma of dark matter, an unseen majority whose gravity sculpted the galaxies we observe, yet whose nature remained elusive. Science had mapped the territory, only to find the map key was written in an unknown language. Faced with these fundamental mysteries, the origin of galactic shapes, the discrepancy between appearance and age, the dominance of invisible matter, the human mind did what it has always done when confronted with the unknown. It began to theorize. It began to propose explanations, build models, and inevitably to disagree. This chapter delves into that intellectual drama, the period where minds divided, grappling with the contradictions and forging the competing theories that would shape our understanding of galactic evolution, attempting to weave the scattered clues into a coherent story of cosmic creation. The most immediate battleground was the question of morphology itself. Why do galaxies look the way they do? Hubble's initial hunch that his tuning fork represented a simple evolutionary sequence, perhaps from elliptical youth to spiral maturity, crumbled under the weight of stellar population data. A new understanding was needed, one that could account for both the shapes we see and the ages of the stars within them. This led to the great theoretical divide between top-down and bottom-up formation scenarios. The top-down theory, often called monolithic collapse, held sway for a time. It envisioned galaxies forming relatively quickly in the early universe, from the gravitational collapse of truly immense, single clouds of primordial gas. The elegance of this model lay in its apparent ability to explain the basic dichotomy. A cloud born with significant rotation would naturally flatten into a disk as it collapsed, conserving angular momentum and setting the stage for a spiral galaxy where stars form slowly over billions of years within that disk. Conversely, a cloud with little initial spin, or one where star formation was incredibly efficient and rapid during the collapse itself, might use up its gas before a disk could fully form, resulting in a more spheroidal distribution of stars, an elliptical galaxy composed primarily of ancient stars born in that initial burst. This seemed to neatly reconcile the shapes with the stellar ages. However, as observational astronomy pushed deeper into the early universe, the top-down picture began to fray. Telescopes like Hubble revealed that the first structures forming were not typically huge, smoothly collapsing clouds, but rather smaller, clumpy, irregular-looking galaxies, often engaged in chaotic interactions. Furthermore, the detailed structure of spiral galaxies, particularly their extended halos containing streams of old stars with diverse origins, seemed difficult to explain solely through a single, rapid formation event. The universe looked messier, more complex than the elegant top-down scenario suggested. This paved the way for the ascendance of the competing theory: hierarchical formation or the bottom-up model. This theory, strongly motivated by cosmological simulations based on the cold dark matter paradigm, which naturally predicted small structures forming first, proposed that galaxy formation is a gradual, cumulative process driven by gravity acting over billions of years. In this view, the universe builds complexity from the ground up. Small fluctuations in the early universe first collapse into small dark matter halos. Gas cools and settles within these halos, forming the first dwarf galaxies. These small galaxies then act as building blocks. Through gravitational attraction, they fall together, orbit each other, collide, and merge, gradually assembling larger and larger structures over cosmic time. The hierarchical model offered compelling explanations for many observed phenomena. It naturally accounted for the prevalence of small, irregular galaxies in the early universe. It explained the existence of stellar streams and disrupted satellite galaxies in the halos of large galaxies like the Milky Way as fossil evidence of this ongoing accretion process. Crucially, it provided a compelling framework for understanding the morphological differences between galaxies as a consequence of their merger history. In this picture, spiral galaxies like ours are viewed as systems that have experienced a relatively quiescent past, dominated by the smooth accretion of gas and perhaps the occasional minor merger with small dwarf galaxies, events insufficient to destroy their fragile rotating disks. Giant elliptical galaxies, on the other hand, are seen as the end products of numerous, often violent, major mergers, particularly the collision and coalescence of two or more large spiral galaxies. Such cataclysmic events, simulations showed, would effectively scramble the ordered rotation of the original disks, randomize stellar orbits through gravitational relaxation, trigger intense bursts of star formation that rapidly consume the available interstellar gas, and ultimately lead to the formation of a large, smooth, gas-poor, bulge-dominated elliptical remnant populated mainly by older stars. Irregular galaxies could represent systems caught in the midst of mergers, remnants of past disruptions, or simply young systems still undergoing initial assembly. The intellectual drama intensified around this dichotomy. Was galaxy formation a rapid event in the early cosmos, top-down, or a slow, cumulative process continuing to the present day, bottom-up? While the weight of observational evidence gradually tilted strongly in favor of the hierarchical model as the dominant paradigm, the debate wasn't entirely settled. Reality is often complex, and elements of both processes might play a role. Perhaps the very dense cores of galaxies formed rapidly early on, monolithically, while their extended disks and halos were built up later through accretion and mergers hierarchically. Minds continued to divide on the relative importance and timing of these mechanisms. Closely related to the merger history debate was the question of nature versus nurture. Is a galaxy's final form primarily determined by its intrinsic properties, established during formation, like its initial mass and angular momentum, or is it heavily sculpted by its environment throughout its life? Observations revealed stark differences between galaxy populations in different cosmic settings. Dense galaxy clusters, the crowded downtown cores of the universe, were found to be dominated by giant ellipticals and gas-poor lenticular galaxies, with relatively few star-forming spirals. In contrast, lower density groups like our own local group, and the even sparser field, isolated regions, showed a much higher fraction of gas-rich, actively star-forming spiral galaxies. This strong correlation between morphology and environment fueled theories focused on nurture. Several mechanisms were proposed by which the cluster environment could transform incoming spiral galaxies. Ram pressure stripping became a leading contender. As a spiral galaxy falls into the incredibly hot, dense plasma, the intracluster medium, that fills the space between cluster galaxies, the pressure of this external gas acts like a powerful headwind, stripping away the galaxy's own colder, less dense interstellar gas from its disk. Without this fuel supply, star formation ceases and the spiral gradually fades, potentially evolving into a passive S0, lenticular, or even eventually an elliptical-like galaxy. Galaxy harassment, involving frequent high-speed, flyby gravitational encounters with other cluster members, could tidally disrupt fragile spiral disks, thickening them and potentially scattering stars into a more spheroidal distribution. Strangulation or starvation offered a slower mechanism, suggesting that simply being cut off from the continuous inflow of fresh, cool gas from the surrounding cosmic web, which is thought to feed ongoing star formation in field galaxies, could cause spirals within clusters to gradually exhaust their internal gas reserves and passively fade over billions of years. The intellectual drama lay in disentangling these complex environmental effects from the intrinsic evolutionary path dictated by a galaxy's merger history. How much of the morphology-density relation is due to mergers being more common in dense environments, favoring elliptical formation, and how much is due to these ongoing environmental stripping and harassment processes transforming spirals after they arrive? Different theoretical camps emphasize different processes, leading to extensive observational campaigns comparing galaxies in diverse environments and at different cosmic epochs, look-back times, to try and determine when and how these transformations primarily occur. Is it nature or nurture that primarily defines a galaxy's destiny? The answer likely involves a complex interplay of both. The mystery surrounding the supermassive black holes, SMBHs, found lurking at the centers of nearly all massive galaxies, including our own Sagittarius A*, opened another major front for theoretical division. How did these behemoths, millions or even billions of times the mass of the Sun, form in the first place? Did they start as smaller black holes formed from the collapse of the very first stars, and then grow steadily over cosmic time by accreting gas and merging with other black holes during galactic collisions? Or did massive seed black holes, perhaps tens or hundreds of thousands of solar masses, form directly from the collapse of enormous gas clouds in the early universe, providing a head start for subsequent growth? Adding to the puzzle was the discovery of tight correlations between the mass of a galaxy's central black hole and large-scale properties of the galaxy itself, particularly the mass and velocity dispersion of its central bulge, the M-sigma relation. This suggested a profound, almost symbiotic relationship, an intimate coevolution. The growth of the central black hole and the growth of the galaxy's bulge seemed inextricably linked, influencing each other through some form of feedback. Theories proliferated, proposing mechanisms by which the black hole could regulate its own growth and that of its host galaxy. As gas flows towards the galactic center, it feeds the black hole, causing it to grow and often shine brightly as an active galactic nucleus, AGN, or quasar. The intense radiation pressure, powerful jets, or slower winds driven by this accretion process could then blow gas out of the galactic center, heating the surrounding interstellar medium, suppressing further star formation in the bulge, and potentially cutting off the black hole's own fuel supply. This feedback loop could explain the observed correlations and why galaxies don't grow indefinitely large. However, the precise physics of how energy couples from the tiny scales near the black hole's event horizon to the vast scales of the entire galaxy remained, and still remains, poorly understood and intensely debated. Minds divided on the dominant feedback mechanisms, radiation versus jets versus winds, and their relative importance in different types and masses of galaxies, and at different cosmic epochs. Even the iconic spiral arms themselves, the defining feature of galaxies like the Milky Way, harbored a persistent theoretical contradiction known as the winding problem. Stars and gas in galactic disks do not rotate like a solid wheel. Inner parts orbit faster than outer parts, differential rotation. If the spiral arms were simply fixed structures composed of the same material moving together, this differential rotation should quickly wind them up tightly, like stirring cream into coffee, causing them to disappear within just a few galactic rotations, a few 100 million years. Yet, spiral arms are clearly observed to persist for billions of years. How? This mystery led to the development of the density wave theory, championed by C.C. Lin and Frank Hsu in the 1960s. This elegant theory proposed that spiral arms are not fixed collections of stars and gas, but rather quasi-stable patterns of higher density that propagate through the galactic disk, much like sound waves move through air or traffic jams move along a highway. Individual stars and gas clouds orbit the galaxy and move through these density waves. As they enter an arm, a region of higher density and stronger gravity, they slow down and bunch up temporarily, increasing the arm's visibility. Gas clouds, in particular, are strongly compressed as they pass through the wave's potential well, triggering the collapse of molecular clouds and initiating bursts of star formation, explaining why bright and young blue stars and HII regions prominently trace the spiral arms. After passing through the arm, stars and gas speed up again in the lower density interarm regions. The pattern itself rotates more slowly and rigidly than the individual components, allowing it to persist for long periods without winding up. While the density wave theory provides a compelling framework for understanding the persistence and appearance of spiral structure, the exact mechanism responsible for generating and sustaining these waves remained a subject of debate. Are they triggered by gravitational instabilities within the disk itself, driven by the galaxy's central bar structure, or perhaps excited by tidal interactions with satellite galaxies? Different theories emphasize different drivers, reflecting the complexity of simulating these delicate, large-scale patterns. These examples illustrate how the initial classification of galaxies, intended to simplify, instead opened a Pandora's box of theoretical challenges and intellectual divisions. From the fundamental question of how galaxies acquire their shapes, to the complex interplay between mergers and environment, the enigmatic role of supermassive black holes and feedback, the pervasive mystery of dark matter, and even the beautiful persistence of spiral arms, astronomers and physicists found themselves grappling with a universe far more intricate and dynamic than previously imagined. The minds remained divided, proposing competing explanations, refining models, and designing new observations to test them, not out of conflict, but out of a shared drive to push the boundaries of understanding. This ongoing intellectual drama, fueled by the contradictions inherent in the data, became the very engine driving scientific progress towards a richer, more nuanced, if ever more complex, picture of our place among the diverse and evolving cities of the cosmos. The universe, newly revealed in its true staggering scale and bewildering diversity, did not simply present astronomers with answers. It presented them with profound questions, deep contradictions, and tantalizing mysteries. Why did galaxies come in such distinct shapes? How did these structures form and evolve over cosmic time? What was the nature of the invisible dark matter that seemed to dominate their mass and govern their motions? The initial awe and disorientation following Hubble's discoveries gave way, inevitably, to the focused, methodical, and relentless pursuit of understanding. Curiosity, faced with the contradictions outlined by competing theories, transformed into action. The investigation began in earnest. This investigation, the active ongoing pursuit of answers to the fundamental questions of galactic origins and evolution, became a central driving force in 20th and 21st century astronomy. It was, and is, a monumental undertaking, requiring not just theoretical insight, but the development of entirely new tools, techniques, and observational strategies. It demanded a dual approach, simultaneously looking inward to map and understand our own Milky Way galaxy from our challenging position embedded deep within it, and looking outward across unimaginable distances to survey the vast population of external galaxies, decipher their properties, and piece together their collective history. The first essential challenge was overcoming the limitations of our internal perspective, the cosmic fog that obscures our view of our own galactic city. Dense clouds of interstellar dust, concentrated along the plane of the Milky Way's disk, act like a thick curtain, absorbing and scattering visible light. This prevents us from seeing more than a few thousand light-years in many directions along the galactic plane, completely hiding the galaxy's core and vast portions of its spiral arms from direct optical view. To map our home, the investigation had to find ways to see through this dust. Astronomers turned to longer wavelengths of electromagnetic radiation, which are far less susceptible to scattering and absorption by tiny dust grains. Radio astronomy became an indispensable tool. Cold, neutral hydrogen gas, the most abundant element in the universe and the primary fuel for star formation, pervades the galactic disk. While invisible to optical telescopes, this gas emits a faint but specific radio signal at a characteristic wavelength of 21 centimeters. By meticulously scanning the sky with large radio telescopes, sensitive receivers tuned to this specific wavelength, astronomers could map the distribution, density, and motion of neutral hydrogen gas throughout the entire Milky Way, effectively tracing the faint outlines of the spiral arms even in regions completely opaque to visible light. Furthermore, by measuring the subtle Doppler shifts in this 21 centimeter emission caused by the gas clouds moving towards or away from us as the galaxy rotates, scientists could construct detailed maps of the galaxy's rotation pattern. It was these radio maps that provided some of the earliest, most compelling evidence for the unexpectedly high orbital speeds of material in the outer galaxy, revealing the gravitational fingerprint of the unseen dark matter halo. Infrared astronomy, particularly with the advent of sensitive detectors and, crucially, space-based telescopes operating above Earth's obscuring atmosphere like IRAS, Spitzer, WISE, and now the James Webb Space Telescope, provided another vital window through the dust. Infrared light penetrates dust more effectively than visible light. This allowed astronomers, for the first time, to peer into the heavily obscured galactic center, revealing the dense cluster of stars orbiting the supermassive black hole Sagittarius A times with astonishing clarity. Infrared observations also excel at detecting the faint glow of cool stars like red dwarfs, which are numerous but optically faint, and the thermal emission from interstellar dust grains warmed by embedded young stars. This makes infrared surveys ideal for mapping the overall stellar mass distribution and pinpointing hidden star-forming regions within the dusty spiral arms. While seeing through the dust was essential, the investigation also required mapping what could be seen in visible light with unprecedented precision. This became the realm of astrometry, the oldest branch of astronomy, focused on measuring the precise positions, distances, and motions of stars. For centuries, this was a painstaking process, limited by the blurring effects of Earth's atmosphere and the difficulty of measuring tiny shifts in stellar positions. The launch of the European Space Agency's Hipparcos satellite in 1989 marked a major leap, providing accurate positions and parallaxes. The tiny apparent shifts in a star's position due to Earth's orbit, used to determine distance for over 100,000 stars. But its successor, Gaia, launched in 2013, utterly revolutionized the field. Gaia is engaged in an ongoing mission to create a dynamic, three-dimensional map of a significant portion of the Milky Way by measuring the positions, distances via parallax with micro-arcsecond accuracy, proper motions, sideways movement across the sky, and radial velocities, motion towards or away from us for over 1 billion stars. This extraordinarily rich dataset is providing an unparalleled view of our galaxy's structure and kinematics. Astronomers are using Gaia data to trace the flow of stars within the disk, identify co-moving groups and stellar streams left over from ancient galactic mergers, precisely measure the galaxy's rotation curve, map the distribution of dust, and refine our understanding of the Milky Way's mass, structure, and formation history with stunning detail. Gaia's investigation is, in essence, transforming our blurry street-level view into a high-resolution, dynamic city map, constructed entirely from within. Simultaneously, the investigation pushed relentlessly outward, aiming to map the vast extragalactic universe, understand the full spectrum of galactic forms and sizes, and piece together their evolutionary history. This required conquering the immense challenge of cosmic distance measurement, extending the cosmic distance ladder step by step into the deep universe. Cepheid variable stars, Hubble's original key, remained crucial for calibrating distances to relatively nearby galaxies, those within about 100 million light-years, where individual pulsating stars could still be resolved, especially with the sharp vision of the Hubble Space Telescope. Establishing accurate distances to these nearby galaxies was essential for calibrating other distance indicators needed to probe farther out. For reaching into the truly deep universe, billions of light-years away, astronomers increasingly relied on an even brighter, though much rarer, standard candle. Type Ia supernovae. These specific types of stellar explosions, resulting from the thermonuclear detonation of white dwarf stars exceeding a critical mass limit in binary systems, were found, observationally, to reach a remarkably consistent peak intrinsic luminosity, making them visible across vast cosmic distances. By discovering these supernovae in distant galaxies, often through dedicated survey telescopes that repeatedly scan large areas of the sky, and carefully measuring their apparent brightness as they faded over weeks, astronomers could calculate their distances, providing crucial anchor points deep within the Hubble flow. It was the comparison of distances derived from Type Ia supernovae with their corresponding redshifts that led to the startling discovery of the universe's accelerating expansion. Redshift itself, the stretching of light waves due to the expansion of space, became arguably the most powerful tool for mapping the large-scale universe. While the precise conversion from redshift to distance depends on cosmological parameters like the expansion rate and the amounts of dark matter and dark energy, measuring a galaxy's redshift provides a direct indication of its distance relative to others and its place in cosmic history. Large-scale redshift surveys, using spectrographs capable of measuring the spectra, and thus redshifts, of thousands of galaxies simultaneously, became a cornerstone of modern cosmology. Projects like the Sloan Digital Sky Survey, SDSS, the 2DF Galaxy Redshift Survey, and more recent efforts like DESI, Dark Energy Spectroscopic Instrument, have meticulously measured the redshifts for millions of galaxies, creating vast three-dimensional maps, revealing the intricate structure of the cosmic web, the interconnected network of galaxy clusters, filaments, and voids with unprecedented clarity. This mapping provided the essential framework for testing theories of structure formation and understanding how galaxy evolution is influenced by large-scale environment. The investigation, however, required more than just knowing where galaxies were. It needed to understand what they were. Spectroscopy, the technique of splitting light into its rainbow of constituent colors or wavelengths, became indispensable for deciphering the physical properties of distant galaxies. The spectrum of a galaxy acts like a fingerprint, encoding a wealth of information. The pattern of dark absorption lines reveals the chemical composition of its stars, how enriched they are with heavy elements forged by previous generations. The overall shape of the continuum spectrum indicates the dominant age and temperature of its stellar population. Young, hot blue stars emit differently than old, cool red stars. Bright emission lines, produced by gas ionized by hot young stars or active galactic nuclei, pinpoint regions of active star formation or black hole accretion. By obtaining spectra for thousands, even millions, of galaxies at different redshifts, and thus different cosmic epochs, astronomers could directly trace the story of galactic evolution. how galaxies built up their stellar mass, accumulated heavy elements, ignited and quenched their star formation over the course of billions of years. Complementing spectroscopy was multi-wavelength imaging, observing galaxies across the entire electromagnetic spectrum. Visible light, captured by telescopes like Hubble, reveals the distribution of stars and the overall morphology. Ultraviolet light, accessible primarily from space, traces the youngest, most massive, hottest stars, providing a direct measure of recent star formation activity. Infrared light, particularly observed by telescopes like Spitzer and JWST, penetrates obscuring dust clouds, revealing hidden star nurseries, mapping the distribution of cooler, older stars that dominate galactic mass, and allowing us to see the most distant, highly redshifted galaxies whose light has been stretched out of the visible range. Radio waves map the reservoirs of cold hydrogen gas, the fuel for future star formation. X-rays expose the extremely hot plasma-filling galaxy clusters and the energetic accretion disks swirling around supermassive black holes. Combining these multi-wavelength views provided a far more complete and unbiased picture of a galaxy's components, activity level, and evolutionary state than visible light alone could ever offer. The persistent, overwhelming mystery of dark matter demanded its own specialized investigative tools, focusing not on emitted light, but on gravitational effects. Measuring galactic rotation curves and stellar velocity dispersions remained crucial for inferring the total mass enclosed within galaxies. Analyzing the dynamics of satellite galaxies and globular clusters orbiting large galaxies like the Milky Way provided probes of the dark matter halo's extent and shape far beyond the visible disk. Studying the confinement of hot, X-ray emitting gas in galaxy clusters offered a way to weigh the entire cluster, confirming the dominance of dark matter on the largest bound scales. Perhaps most powerfully, gravitational lensing. In both its strong form, creating dramatic arcs and multiple images, and weak form, creating subtle statistical distortions in the shapes of background galaxies, it became a primary technique for directly mapping the distribution of total mass, both dark and visible in foreground galaxies and clusters, independent of assumptions about their dynamical state. Finally, the investigation increasingly leveraged the power of the virtual universe through cosmological simulations. Using the most powerful supercomputers available, physicists and astrophysicists could create complex models that simulated the evolution of large volumes of the universe, starting from the initial conditions inferred from the cosmic microwave background and incorporating the known laws of physics, including gravity, gas dynamics, thermodynamics, star formation, stellar feedback, black hole growth, and the assumed properties of dark matter and dark energy. These simulations allowed scientists to watch structure form in silico to see how dark matter halos collapse and merge, how gas cools and fragments within them to form stars and galaxies, how those galaxies interact, collide, and evolve over billions of virtual years. By comparing the statistical properties of the simulated galaxy populations, their numbers, sizes, shapes, colors, clustering patterns, to the actual observed universe revealed by large surveys, researchers could test the validity of their underlying cosmological model, for example, the standard lambda cold dark matter model, and gain insights into the complex physical processes governing galaxy formation that are often difficult to disentangle from observations alone. Simulations became an essential tool for interpreting observations and testing theoretical ideas. This vast, multifaceted investigation, mapping our galaxy from within, charting the extragalactic realms, measuring distances and masses, dissecting light across all wavelengths, probing invisible matter through gravity, and simulating cosmic evolution in computers, represents the collective human pursuit of answers. It is a testament to our species' relentless curiosity, our ingenuity in developing tools to extend our senses across unimaginable scales, and our willingness to confront and embrace a universe far stranger and more magnificent than we initially knew. The clues and fragments gathered through this ongoing pursuit form the basis of our current understanding, allowing us to place our ordinary Milky Way within the extraordinary context of the cosmos and its colossal inhabitants. The investigation was vast, multi-pronged, and relentless, driven by the profound mysteries uncovered in the early exploration of the extragalactic universe. Astronomers deployed an arsenal of tools and techniques mapping our own galaxy from within, using wavelengths that pierced the obscuring dust, extending the cosmic distance ladder outwards with standard candles like Cepheids and supernovae, dissecting the faint light of distant galaxies with spectroscopy, weighing cosmic structures through their dynamics and gravitational lensing, and comparing all of this to sophisticated cosmological simulations. Now, after decades of this meticulous pursuit, what verifiable evidence, what crucial data, what enduring clues and fragments has this grand investigation yielded? What does the universe, measured and quantified, actually tell us about our place and the scale of its inhabitants? The data streams converged, reinforcing a picture that was both humbling and awe-inspiring. First, let's consider the data defining our home. The Milky Way. Precise measurements, particularly from astrometric missions like Gaia, combined with radio and infrared mapping, solidified its status as a relatively large, but ultimately typical barred spiral galaxy. The data points paint a specific portrait. The stellar disk, the main body containing the spiral arms and most of the young stars, spans approximately 100,000 light-years in diameter. While vast on a human scale, this number sits comfortably within the observed range for spiral galaxies across the cosmos. The disk is remarkably thin, perhaps only 1,000 light-years thick in our solar neighborhood, emphasizing its flattened, rotating structure. Within this volume reside an estimated 100 to 400 billion stars, a number derived from star counts in surveyed regions extrapolated to the whole galaxy, constrained by models of stellar populations and mass distribution. The associated number of planets, based on statistical results from exoplanet surveys like Kepler, is likely even higher, potentially reaching into the trillions, with billions estimated to be roughly Earth-sized and orbiting within the habitable zones of their stars. These numbers establish the Milky Way as a rich and populous system, yet still fall short of the counts inferred for the true cosmic giants. The total mass of the Milky Way, the crucial number dominated by the invisible dark matter, has been painstakingly estimated through various dynamical methods. Gaia's precise measurements of stellar motions, the rotation curve traced by gas clouds, and the orbits of satellite galaxies and globular clusters all provide gravitational probes of the underlying mass distribution. The converging data suggest a total mass of roughly 1 to 1.5 trillion times the mass of our Sun. 1 to 1.5 x 10 is less than sup, is greater than 12 is less than sup is greater than m. Crucially, the data confirms that only about 10% of this mass resides in the visible stars, gas, and dust. The remaining 90% is locked away in the vast, unseen dark matter halo. This finding, replicated in galaxy after galaxy, became a cornerstone piece of evidence solidifying the dark matter paradigm. The galaxy's luminosity, its total light output, is measured to be around 10 to 20 billion times the luminosity of our Sun, again typical for a spiral of its size and mass. Its overall colour, a mix of blue light from young stars in the arms and redder light from older stars in the bulge and halo, reflects its ongoing but moderate rate of star formation. Data from infrared and ultraviolet observations pin down this star formation rate to approximately 1 to 2 solar masses worth of new stars per year, a sustainable pace characteristic of a mature, stable spiral galaxy, neither undergoing a frantic starburst nor having faded into quiescence. These key data points, size, star count, mass, luminosity, star formation rate collectively establish the Milky Way's baseline. They provide the quantitative foundation for the statement that our galaxy, while magnificent from our perspective, holds a relatively average position in the cosmic census of large galaxies. It serves as the essential reference point against which the extremes can be measured. Now, let's turn to the data revealing those extremes, the clues and fragments that define the cosmic giants. Surveys mapping galaxy clusters consistently identified the brightest cluster galaxies, BCGs, typically giant elliptical galaxies residing at the gravitational center of these dense environments. The data gathered on these behemoths paints a starkly different picture. Their sizes are truly colossal. While direct measurement is complicated by their diffuse, extended halos that blend into the intra-cluster light, estimates for the stellar extent of the largest BCGs reach diameters of 1 to 2 million light-years, 10 to 20 times the span of the Milky Way's stellar disk. Some, like IC 1101, possess extraordinarily vast, low-surface brightness envelopes that might extend outwards for up to 6 million light-years, though defining a precise edge is difficult. This data confirms they are not just slightly larger, but occupy a fundamentally different scale class. Their stellar content is correspondingly immense. Direct star counts are impossible, but estimates based on luminosity, mass modeling, and stellar population synthesis suggest the largest BCGs can contain tens of trillions, perhaps even up to 100 trillion stars. This represents hundreds, even 1,000 times, the stellar population of the Milky Way. These galaxies are galactic empires built from the accumulated stars of countless merged predecessors. Their total masses, dominated again by dark matter, are staggering. Dynamical measurements within clusters, analyzing galaxy motions, hot gas temperatures via X-rays, and gravitational lensing patterns consistently yield total mass estimates for the richest clusters, reaching quadrillions. 10 is less than sup, is greater than 15, is less than sup is greater than sup is greater than, of solar masses. The central BCG, being the anchor of this mass, possesses a dark matter halo far exceeding that of the Milky Way, potentially reaching tens or even hundreds of trillions of solar masses. The data from lensing, in particular, provides detailed maps of this mass distribution, confirming that these giants reside within the deepest gravitational wells in the universe. Their luminosities reflect their enormous stellar populations, often exceeding the Milky Way's light output by factors of 10 or more. However, their light is typically redder, dominated by ancient stellar populations, indicating very low or non-existent current star formation rates. Spectroscopic data confirms the lack of emission lines associated with young stars or ionized gas, painting a picture of red and dead systems that completed most of their star building billions of years ago. The data on their internal structure and dynamics further differentiates them. Velocity dispersion measurements show stars moving at high speeds in random, elliptical orbits, unlike the ordered rotation seen in spiral disks. Their light profiles are smooth and centrally concentrated, lacking the sharp features of spiral arms or dust lanes. Data on their central supermassive black holes reveals objects far more massive than Sagittarius A*, sometimes reaching tens of billions of solar masses, reflecting their history of numerous mergers. These contrasting data sets, size, star count, mass, luminosity, star formation rate, kinematics provide the undeniable, quantitative evidence for the vast difference between average spirals like the Milky Way and the giant ellipticals that dominate cluster cores. The comparison is not just one of degree, but almost of kind. They represent different evolutionary endpoints, shaped by vastly different environments and histories. Beyond the properties of individual galaxies, the investigation yielded crucial data on the large-scale distribution of galaxies. Redshift surveys like SDSS mapped the positions of millions of galaxies, revealing the cosmic web. The data showed that galaxies are not randomly scattered, but trace out a filamentary network surrounding vast, underdense voids. Galaxy clusters, containing hundreds to thousands of galaxies, reside at the dense intersections of these filaments. This mapped structure, statistically consistent across billions of light-years, provided strong support for the hierarchical formation model within a cold dark matter cosmology. The data itself, the precise coordinates and redshifts of countless galaxies, became the evidence, the fossil record of cosmic structure formation. Crucially, the data confirmed the morphology-density relation. Elliptical galaxies are preferentially found in the dense cluster cores, while spiral galaxies are more common in lower density groups and filaments. This statistical correlation, quantified through careful analysis of large survey datasets, provided strong evidence that environment plays a key role in shaping galactic evolution, lending weight to theories involving mergers and environmental stripping mechanisms. Data from gravitational lensing, beyond just measuring mass, provided further clues. The prevalence and strength of lensing effects observed around massive galaxies and clusters matched the predictions of models dominated by cold dark matter, providing independent support for this paradigm. Weak lensing surveys, measuring the subtle, coherent distortions in the shapes of millions of background galaxies, allowed astronomers to create maps of the intervening dark matter distribution on large scales, directly visualizing the invisible cosmic web. Data gathered across cosmic time by observing galaxies at high redshifts using telescopes like Hubble and JWST provided direct fragments of the evolutionary story. These observations confirmed that galaxies in the early universe were indeed generally smaller, bluer, more irregular, and formed stars at much higher rates than galaxies today. Astronomers could literally watch the buildup of stellar mass over cosmic history, measure how chemical enrichment proceeded, and track the emergence of different galactic morphologies. This look-back data provided crucial constraints on theoretical models, confirming the general picture of hierarchical growth while also revealing complexities and surprises, like the unexpectedly early appearance of massive galaxies, that continue to drive research. Finally, the investigation yielded precise data on the cosmic expansion history itself. Measurements of Type Ia supernovae at various redshifts allowed astronomers not only to confirm the expansion, but to discover its acceleration. Data from the cosmic microwave background, CMB, the relic radiation from the Big Bang, provided an incredibly precise snapshot of the universe at recombination about 380,000 years after the beginning, revealing the initial density fluctuations that seeded all structure and allowing for precise measurements of fundamental cosmological parameters, the total density of matter and energy, the proportion of dark matter, dark energy, and normal matter, the age of the universe currently estimated at 13.8 billion years, and the geometry of space. These cosmological parameters, derived from CMB data, for example, from the WMAP and Planck satellites, and corroborated by supernova data and large-scale structure surveys, provide the overarching framework within which all galactic comparisons must be understood. The data tells us we live in a lambda cold dark matter LCDM universe, spatially flat, dominated by dark energy, L to 70%, and cold dark matter, 25%, with normal baryonic matter making up less than 5%. This composition dictates the rate of expansion, the growth of structure, and the ultimate fate of the cosmos. In summary, the data gathered through decades of investigation provides a rich, quantitative tapestry. It confirms the Milky Way's status as an average but substantial barred spiral. It reveals the existence of colossal giant elliptical galaxies, orders of magnitude larger and more massive, typically residing in dense cluster environments. It establishes the overwhelming dominance of invisible dark matter in governing galactic structure and dynamics. It maps the cosmic web, linking galaxy evolution to large-scale environment. It traces the history of galactic assembly back through cosmic time, and it defines the fundamental cosmological parameters describing the expanding, accelerating universe we inhabit. These clues and fragments, meticulously collected and analyzed, form the bedrock of our current understanding, reinforcing the realism of our cosmic narrative while simultaneously highlighting the profound mysteries, like the nature of dark matter and dark energy, that still await explanation. The data speaks, and its story is one of scale, evolution, and connection across the vastness. Our investigation, launched in pursuit of understanding our place among the galaxies, has yielded a universe brimming with data, yet shrouded in profound mystery. We meticulously gathered clues, the distances to island universes measured by flickering Cepheid stars and exploding supernovae, the diverse shapes of galaxies classified by Hubble's eye, the motions of stars within them revealing speeds that defied explanation, the large-scale distribution mapped by redshifts, painting a cosmic web, the evidence mounted, confirming the Milky Way's comfortable averageness against the backdrop of colossal giants like IC 1101, and suggesting a dynamic history of hierarchical growth through mergers within an expanding cosmos. But woven through all this data, through every observation and calculation, ran threads of deep contradiction, persistent enigmas that hinted at something more fundamental, something hidden beneath the luminous surface of reality. The conflict between galactic morphology and stellar age, the puzzle of diverse formation paths, the intimate yet poorly understood link between galaxies and their central black holes, these pointed towards complexities beyond our initial grasp. And towering above them all was the undeniable, gravitational evidence for dark matter, an invisible substance comprising the vast majority of cosmic mass, whose nature remained utterly unknown. It is here, in confronting these persistent unknowns, that we uncover the deeper mystery. The hidden truth is not merely that dark matter exists, or that galaxies reside within a cosmic web. The truly profound realization, the truth lurking beneath the surface of all our observations, is that the visible universe, the realm of stars and gas and light that we have painstakingly mapped, is merely a secondary structure, a luminous decoration suspended within and governed entirely by an invisible universe whose properties we are only beginning to comprehend. The reality we see is not the primary reality. Let's delve deeper into the staggering implications of dark matter's dominance. We establish that rotation curves of spiral galaxies demand that some 85% of their mass must be non-luminous. This isn't just a minor correction, it's a fundamental redefinition of what a galaxy is. A galaxy like the Milky Way or Andromeda is not primarily a disk of stars. It is, first and foremost, an immense, roughly spherical halo of dark matter extending hundreds of thousands, perhaps millions, of light-years into space. The visible component, the bulge, the disk, the spiral arms, all the stars and gas we associate with the galaxy's identity, is merely the baryonic, normal matter that has managed to cool, condense, and settle into the gravitational potential, well, at the very center of this vast, unseen structure. The visible galaxy is like a small amount of sediment gathered at the bottom of an enormous, invisible ocean. Its shape, its size, its rotation speed are all dictated primarily by the gravitational field of the surrounding dark matter halo. When we compare the Milky Way to a giant elliptical like IC 1101, we are not just comparing their stellar content, we are, more fundamentally, comparing the properties of the colossal dark matter halos within which they are embedded. IC 1101's immense size and mass are overwhelmingly due to its dark matter halo. which likely dominates the entire core of the Able 2029 cluster. The visible stars are just the luminous frosting on an enormous dark cake. This hidden truth fundamentally alters our understanding of galaxy formation. The hierarchical model is primarily a story about how dark matter halos form and merge over cosmic time. Because dark matter does not interact with light, it was not subject to the radiation pressure that kept normal matter smooth in the very early universe. Thus, dark matter could begin collapsing gravitationally much earlier, forming the first small mini-halos. These mini-halos then merged to form larger halos, and those merged to form still larger ones, creating the underlying scaffolding of the cosmic web. Normal baryonic gas was then drawn into the gravitational wells of these pre-existing dark matter halos. As the gas fell in, it could cool by radiating away energy, unlike dark matter, allowing it to condense further, form stars, and settle into rotating disks at the halo centers. The visible galaxy we see is therefore a secondary structure, its formation and evolution intimately coupled to, but distinct from, the assembly history of its host dark matter halo. The deeper mystery is that the primary engine of cosmic structure formation is a substance whose nature remains completely unknown. We infer its existence with high confidence from its gravitational effects, flat rotation curves, cluster dynamics, gravitational lensing, the structure of the cosmic microwave background, but we have yet to directly detect a dark matter particle in any laboratory experiment, despite decades of searching. Is it a WIMP, an axion, a sterile neutrino, or something entirely unimagined? Does it interact with itself? Does it decay? The answers remain elusive, forming a gaping hole at the heart of our cosmological model. This ignorance is the hidden truth. We understand the effects of the universe's dominant matter component, but not its essence. Flowing directly from the dominance of dark matter is the profound significance of the cosmic web. The vast network of clusters, filaments, and voids revealed by galaxy redshift surveys is not just a map of where galaxies happen to be. It is the physical manifestation of the underlying dark matter distribution, the gravitational landscape sculpted over billions of years. Galaxies form within this web, primarily along the filaments where gas can efficiently cool and condense within dark matter halos. Clusters form at the dense intersections, the major gravitational crossroads. The voids, vast regions largely devoid of dark matter, remain correspondingly empty of luminous galaxies. The hidden truth here is the extent to which a galaxy's entire life story, its formation, its growth rate, its morphology, its star formation history, its ultimate fate is profoundly influenced, perhaps even predetermined, by its location within this larger cosmic architecture. A galaxy is not an isolated island. It is a node within an interconnected network, constantly influenced by the flow of matter and the gravitational tides of its surroundings. Consider the contrast. A galaxy forming in relative isolation within a cosmic void might experience a quiet history, slowly accreting gas from the surrounding intergalactic medium, maintaining a stable disk, and continuing to form stars at a moderate pace for billions of years, much like our own Milky Way seems to have done. Its evolution is largely governed by its internal processes. Now, consider a galaxy forming within, or falling into, a dense galaxy cluster. Its experience is entirely different. It is subject to frequent high-speed gravitational encounters, harassment, with other galaxies that can disrupt its disk. It moves through the hot, dense intracluster medium, experiencing ram pressure that strips away its cold gas, quenching star formation. It is much more likely to undergo major mergers with other galaxies, events that can fundamentally transform its structure from a spiral into an elliptical. Its evolution is dominated by external, environmental forces. The deeper mystery revealed by the cosmic web is the realization that environment is destiny for galaxies, to a large extent. The striking difference between the population of blue, star-forming spirals found predominantly in the field and the population of red, passive ellipticals found predominantly in cluster cores is a direct consequence of this environmental influence playing out over cosmic time. The colossal size and ancient stellar populations of giant ellipticals like IC1101 are not intrinsic properties they were born with, but the cumulative result of their privileged position at the bottom of deep gravitational wells within the densest nodes of the cosmic web, allowing them to relentlessly consume their neighbors for billions of years. The hidden truth is that comparing the Milky Way to IC1101 is not just comparing two objects, but comparing two entirely different ecological niches within the cosmic landscape. One is a resident of the quiet galactic suburbs. The other is the product of the intense competitive environment of the cosmic metropolis core. Their profound differences in scale and form reflect their profoundly different life experiences within the overarching structure of the cosmic web, itself dictated by the unseen scaffolding of dark matter. This leads us to the final, and perhaps most unsettling, aspect of the deeper mystery: the nature and influence of dark energy. If dark matter provides the gravitational glue holding structures together, dark energy appears to be the anti-gravity force driving the universe apart on the largest scales, causing the expansion to accelerate. Discovered through observations of distant supernovae appearing fainter than expected, its existence is now firmly established through multiple lines of evidence, including the cosmic microwave background and the large-scale distribution of galaxies. The hidden truth revealed by dark energy is that the universe's ultimate fate seems dominated by a substance or property of space-time that we understand even less than dark matter. It appears to constitute nearly 70% of the universe's total energy density, yet its fundamental nature, whether it's Einstein's cosmological constant, an intrinsic energy of empty space, or some dynamic field, remains profoundly mysterious. Dark energy operates on the largest scales, acting repulsively to drive galaxies and clusters farther apart over time. While gravitationally bound systems like our local group or the Coma cluster will remain intact internally, the accelerating expansion means that the space between these bound structures is stretching at an ever-increasing rate. The consequence is cosmic isolation. Distant superclusters, currently receding from us, will eventually be carried away faster than light can travel across the expanding gap. Their light will redshift beyond detectability, and they will effectively disappear beyond our cosmic horizon. The deeper mystery here is twofold. First, what is this dominant component of the universe that dictates its ultimate destiny? Second, what does its existence imply about the relationship between structures like the Milky Way and the giants found in distant clusters? It implies that the cosmic web we observe today is, in a sense, already beginning to dissolve on the larger scales. The connections are being stretched, the communication lines severed by accelerating expansion. Our ability to compare our galaxy to others across vast distances is a feature of the current cosmic epoch, but perhaps not a permanent one. The hidden truth is that the universe might be becoming lonelier over time, its grand structures slowly isolating themselves from one another. Therefore, the deeper mystery, the hidden truth revealed by decades of investigation, is that the universe we perceive, the luminous galaxies, the visible structures, is merely the surface layer of a far more profound and largely invisible reality. It is a reality dominated by dark matter, which provides the gravitational framework, structured by the cosmic web, which dictates evolutionary pathways based on location, and ultimately governed by dark energy, which drives cosmic expansion and determines the universe's fate. Our comparison between the Milky Way and the cosmic giants is fundamentally shaped by these unseen forces and structures. The visible differences in size, shape, and history are merely the luminous manifestations of a deeper, darker, and still largely enigmatic cosmic play unfolding across billions of years. Understanding these hidden truths is the key to truly comprehending our place within the grand, and often invisible, architecture of existence. Our journey outward, seeking to place our Milky Way within the grand tapestry of the cosmos, has led us through layers of deepening understanding, but also profound mystery. We started with the comfortable, intuitive feeling of our galaxy's immense scale, only to confront the humbling hook, its undeniable averageness when compared to the true giants of the universe. We established our setting within this familiar barred spiral, mapping its structure, acknowledging its quiet beauty, and recognizing its likely history of steady growth within the relatively calm local group. We then retraced the pivotal discovery by Edwin Hubble, the moment the faint smudges called nebulae were revealed as distant island universes, shattering the illusion of cosmic solitude and sparking the narrative of comparison. The first human response was a mixture of awe, disbelief, and an urgent need to classify, to bring order to this suddenly vast and populated reality. But this very act of classification quickly unearthed contradictions. Visual sequence of Hubble's tuning fork clashed with the ages derived from stellar populations, challenging simple evolutionary theories. Minds divided, proposing competing models. Did galaxies form rapidly from monolithic collapse, or build slowly through hierarchical mergers over billions of years? The investigation intensified, employing sophisticated tools to gather data across cosmic time and distance, yet uncovering further enigmas, most notably the pervasive gravitational dominance of unseen dark matter. This led us to the deeper mystery, the hidden truth that the visible universe is merely luminous foam on a vast dark ocean, like its structure and evolution governed by invisible matter and shaped by its place within the cosmic web. Now, amidst this landscape rich with knowledge yet shadowed by fundamental unknowns, we arrive at the heart of the transformation, the true turning point in our entire cosmic narrative. This isn't the discovery of a single object or a specific process within galaxies. It is the culmination, the synthesis, the moment when the accumulated weight of evidence forced a paradigm shift so profound that it didn't just refine our understanding of galaxies, it redefined the very nature of the universe itself and our place within its unfolding story. This turning point, primarily anchored in the groundbreaking work of Edwin Hubble and his contemporaries in the 1920s, represents the peak in tension where the old, static, contained cosmos definitively broke, giving way to the dynamic, expanding, and vastly larger reality we inhabit today. Let us return, with deeper appreciation now, to that pivotal moment. The early 20th century saw astronomy grappling with the enigmatic nature of the spiral nebulae. The Great Debate highlighted the central tension. Were these objects relatively small gas clouds within our Milky Way, or colossal star systems lying at unimaginable distances? The lack of a reliable method for measuring distances beyond our immediate stellar neighborhood held the answer captive. The tension lay in the stakes. One possibility confined us to a single, perhaps unique galactic island. The other cast us adrift in an ocean potentially teeming with them. The critical breakthrough, the key that unlocked the cosmic scale, came from Edwin Hubble's meticulous observations of Cepheid variable stars within the Andromeda Nebula, M31, using the powerful 100-inch Hooker telescope at Mount Wilson. Building upon Henrietta Leavitt's discovery of the period luminosity relationship for these pulsating stars, Hubble had found his standard candle. By measuring the pulsation periods of Cepheids in Andromeda, he could determine their true intrinsic brightness. Comparing this known brightness to their faint apparent magnitude as observed from Earth, he could calculate their distance using the fundamental inverse square law of light. The numbers Hubble derived, first presented decisively in 1924 and 1925, were nothing short of revolutionary. His calculations placed Andromeda nearly 1 million light-years away, a figure later refined, but already vastly larger than any previous estimate. This distance utterly dwarfed the accepted size of the Milky Way, proving conclusively that Andromeda was not a local phenomenon but a separate, colossal galaxy. An island universe in its own right, comparable in scale to our own home. This was the turning point, the definitive proof of extragalactic scale. The moment the conceptual walls of the universe didn't just expand, they dissolved. The tension of the great debate broke. The paradigm shifted irrevocably. Our galaxy, once the entirety of creation, became just one citizen in a potentially infinite cosmic nation. Awe, humility, and a sense of profound intellectual vertigo washed over the scientific community. The universe was suddenly, undeniably, vastly larger and more populated than ever conceived. The very framework for asking questions about our place had changed forever. But this realization, as monumental as it was only the first act of this transformative turning point. It answered the fundamental questions of where and what, revealing the existence and nature of other galaxies. Almost immediately, however, building upon this new foundation of cosmic distance, came the second, equally profound revelation, addressing the when and how the discovery that this vastly larger universe was not static. Hubble, having established reliable distances to several nearby galaxies using Cepheids, turned his attention back to the puzzling redshift data that Vesto Slipher had been accumulating. Slipher had shown, through careful spectroscopic measurements, that most of the spiral nebulae exhibited spectral lines shifted towards the red end of the spectrum, indicating they were moving away from us at significant speeds, sometimes thousands of kilometers per second. Now, Hubble could combine these measured recessional velocities with his new robust distance measurements for a sample of galaxies. In 1929, he published his landmark finding. A clear, linear relationship existed between a galaxy's distance and its recessional velocity. The farther away a galaxy is, the faster it appears to be receding from us. This systematic pattern, observed consistently in all directions, became known as Hubble's law. Its implication was staggering. The entire universe is expanding. This wasn't simply galaxies flying randomly apart through space after some explosion. The law implied something far deeper. The very fabric of space-time itself was stretching, carrying the galaxies along with it, like points on the surface of an inflating balloon. An observer on any galaxy would see all other distant galaxies receding from them in accordance with the same law. There was no privileged center to this expansion. This second realization was, in many ways, even more transformative than the first. It shattered the millennia-old philosophical assumption of an eternal, unchanging cosmos. The universe was not a static stage. It was a dynamic, evolving entity. It had a history. If it was expanding now, then tracing that expansion backward in time implied that in the distant past, the universe must have been incredibly smaller, denser, and hotter. This line of reasoning led directly, through the work of theorists like Georges Lemaitre, who had predicted such an expansion from Einstein's equations even before Hubble's confirmation, to the conceptual framework of the Big Bang, the idea that the universe originated from an extremely hot, dense primordial state approximately 13.8 billion years ago, and has been expanding and cooling ever since. The turning point, therefore, was this powerful dual revelation. The discovery of extragalactic scale which populated the universe, and the discovery of cosmic expansion which gave it a history and a dynamic nature. Occurring in rapid succession in the 1920s, these two paradigm shifts completely demolished the old cosmological framework and laid the essential groundwork for virtually all of modern astrophysics and cosmology. Everything changed in the wake of this turning point. The fundamental questions astronomers pursued shifted dramatically. It was no longer sufficient to merely map the stars within the Milky Way or classify the shapes of galaxies. The new frontiers became understanding the universe as a whole, mapping the large-scale structure. How did these billions of galaxies arrange themselves within the expanding spacetime? What patterns did they form? This led to the discovery of the cosmic web. Understanding galaxy evolution. If the universe itself was evolving, how did galaxies form and change within that evolving context? How did the diverse morphologies arise over cosmic time? How did giants like IC 1101 assemble their mass, probing cosmic origins and fate? If the universe began with a big bang, what were the precise initial conditions? How did the first stars and galaxies ignite in the cosmic dark ages? What is the ultimate fate of this ongoing expansion, especially in light of the later discovery of dark energy's acceleration? The very act of comparing the Milky Way to other galaxies was fundamentally transformed by this turning point. Our galaxy was no longer just a static object to be compared structurally to others as they exist now. It became an object possessing a deep cosmic history, situated within an evolving universal context. Comparing it to distant galaxies, seen as they were billions of years ago due to light's finite travel time, became a powerful tool for tracing that evolution, for understanding how typical or atypical our own galaxy's developmental path has been relative to the broader cosmic population across time. The comparison gained a temporal dimension, becoming a study in galactic archaeology. This new framework, born from the turning point, resonated deeply with the contradictions and mysteries that had already begun to emerge. The puzzling diversity of galaxy types, which seemed inexplicable in a static universe, could now potentially be understood as different stages or outcomes of evolutionary processes, like hierarchical merging, playing out within the expanding cosmic web. The inference of pervasive dark matter, initially derived from galactic rotation curves, fit naturally into cosmological models, where this invisible substance provides the essential gravitational seeds around which galaxies condense and grow within the expanding spacetime fabric. The pieces began to fall into place, not resolving all mysteries, but providing a coherent, testable structure for addressing them. The transformation was absolute. Before Hubble's dual discoveries, cosmology was largely confined to the realm of philosophy or highly theoretical mathematics, lacking strong observational grounding. Afterward, it became a vibrant observational science, driven by empirical data gathered from the faint light of distant galaxies traveling across an expanding universe. The telescope became a veritable time machine, and the redshift became its cosmic clock. The peak in tension occurred precisely in that transition, in the struggle to accept a reality that contradicted centuries of intuition and established thought. The universe presented data Cepheid distances, confirming vast scales, systemic redshifts confirming universal expansion that demanded a radical revision of the cosmic map. The human mind, initially resistant due to the sheer scale and philosophical implications, was ultimately compelled by the weight of evidence to abandon its comfortable, geocentric, and later galactocentric assumptions and embrace a universe far stranger, larger, older, and more dynamic than ever conceived. This intellectual struggle, this forced expansion of perspective against the inertia of prior belief, was the turning point. From this new vantage point, established in the 1920s, all subsequent investigations into the nature of galaxies, their formation, their evolution, and their place within the large-scale structure flowed naturally. The mapping of the cosmic web, the detailed study of galaxy populations in clusters versus voids, the sophisticated modeling of mergers and feedback processes, the ongoing search for the nature of dark matter and dark energy all are direct consequences of accepting the fundamental extragalactic, expanding reality revealed during this pivotal era. Our comparison tonight, placing the average Milky Way alongside the giant IC 1101, is only possible, only meaningful, because of this turning point. Without Hubble's revelations, IC 1101 would likely still be catalogued as just another faint, fuzzy nebula, its true nature, distance, and colossal scale remaining utterly unknown and unimaginable. The turning point gave us not only the astonishing knowledge that such giants exist, but, more importantly, the very conceptual and observational framework, the expanding universe, the cosmic distance ladder. The models of galactic evolution within a Big Bang cosmology needed to understand them, measure them, and place both them and ourselves within the grand unfolding narrative of cosmic history. It was the moment our local perspective finally shattered, allowing us to perceive, for the first time, the true, breathtaking, and dynamically evolving landscape of the entire observable universe. The turning point was absolute. In the span of just a few years in the 1920s, humanity's conception of the universe fractured and reformed into something immeasurably larger, older, and more dynamic than ever before conceived. Edwin Hubble's twin revelations first, the irrefutable proof that spiral nebulae like Andromeda were distant island universes, entire galaxies comparable to our own Milky Way, and second, the systematic recession of these galaxies, revealing an expanding cosmos, were not merely additions to astronomical knowledge, they were a fundamental paradigm shift, a tearing down of ancient walls. Like dropping a stone into a perfectly still pond, these discoveries sent ripples outward, immediate and powerful consequences that fundamentally altered the course of scientific inquiry, technological development, and even our philosophical understanding of existence itself. The first, most immediate consequence was the birth of extragalactic astronomy as a distinct field of study. Prior to Hubble's work, astronomy was largely concerned with objects within the Milky Way, stars, planets, nebulae, clusters. The possibility of island universes was debated, but lacked empirical grounding. Hubble's distance measurement to Andromeda instantly validated this hypothesis and opened up an entirely new, almost infinitely larger territory for exploration. Suddenly, the primary focus for many astronomers shifted outward. The questions multiplied. How many galaxies were there? What were their properties? How were they distributed? Were they all similar, or did they come in different fundamental types? The consequence was a reorientation of the entire discipline, a collective turning of telescopes and minds toward the vast, newly revealed extragalactic realm. Research programs were initiated, observing time allocated, careers dedicated to mapping and understanding this cosmic archipelago. Flowing directly from this was the profound consequence of realizing the look-back time inherent in observing these distant objects. Light travels incredibly fast, but the distances to other galaxies are so immense that even light takes millions or billions of years to cross them. This wasn't just a curious fact, it became a revolutionary tool. The consequence was the transformation of the telescope into a time machine. When astronomers observed a galaxy millions of light years away, they weren't seeing it as it is now, but as it was millions of years ago, when that light began its journey. Looking at galaxies billions of light years away meant looking billions of years into the past, back towards the infancy of the universe. This realization had immediate and dramatic consequences for understanding galactic evolution. The competing theories of formation, monolithic collapse versus hierarchical merging, could now be tested directly through observation. By systematically surveying galaxies at different distances, and therefore different look-back times, astronomers could literally watch galaxies evolve over cosmic history. Deep field observations, pioneered by the Hubble Space Telescope decades later, but conceptually enabled by this initial turning point, provided stunning confirmation. The distant, early universe did look different. It was populated by smaller, bluer, more irregular, and more actively star-forming galaxies than we see nearby today. This provided strong, direct, observational support for the hierarchical, bottom-up model, suggesting that large, structured galaxies like the Milky Way and giant ellipticals were indeed assembled gradually over billions of years through the merging of smaller precursors. The consequence wasn't just finding more objects, it was uncovering the story of their creation, written in ancient light arriving from across space-time. The static, classified picture of Hubble's tuning fork immediately gave way to a dynamic, historical narrative. The sheer faintness and apparent smallness of these distant galaxies demanded an immediate technological consequence: the relentless drive for larger and more powerful telescopes. Hubble's own discoveries were made possible by the then new 100-inch Hooker telescope, but to probe deeper, to see fainter galaxies farther back in time, required even greater light-gathering power and sharper resolution. This spurred the design and construction of progressively larger instruments throughout the 20th century, like the 200-inch Hale telescope on Palomar Mountain, and later the Keck telescopes, the Very Large Telescope, APLT, and space-based observatories like Hubble and JWST. Each new generation of telescopes pushed the frontiers of observation deeper, fueled by the questions ignited by the initial discovery of the extragalactic universe. Alongside larger apertures came the need for more sensitive detectors. The transition from relying on the human eye at the eyepiece to long-exposure photographic plates, and finally to highly efficient electronic detectors like charge-coupled devices, CCDs, was largely driven by the challenge of capturing the feeble light from distant galaxies. These technological advances not only allowed astronomers to see fainter objects, but also enabled precise quantitative measurements of brightness, color, and spectra essential for deciphering galactic properties. The consequence of looking farther was the constant innovation required to capture those faint whispers of light. The discovery of cosmic expansion via Hubble's law had equally profound and immediate consequences. Firstly, it provided the fundamental framework for understanding galactic redshifts. The observed redshift was no longer just an unexplained velocity. It was a direct measure of the universe's expansion and, through Hubble's law, a powerful tool for estimating cosmic distances on the largest scales. This cemented the foundation of the cosmic distance ladder and enabled the creation of the first large-scale three-dimensional maps of the universe. The consequence was the ability to chart not just the positions, but the vast structure, the filaments, clusters, and voids of the cosmic web. Secondly, the undeniable reality of expansion pointed directly backward in time towards a beginning, the Big Bang. While the detailed theory would take decades to develop and confirm, for example, through the discovery of the cosmic microwave background, the immediate consequence of Hubble's law was the shattering of the prevailing steady-state or eternal universe paradigm. The universe had a history. It had an origin. It was evolving. This shifted cosmology from a largely philosophical or static mathematical exercise into a dynamic, historical science focused on understanding the universe's birth, evolution, and ultimate fate. Questions about nucleosynthesis, the formation of the first light elements, the formation of the first stars and galaxies, and the nature of the initial state became central pursuits of theoretical and observational physics. The consequence was the birth of physical cosmology as we know it. Thirdly, the expansion immediately raised questions about the universe's geometry and destiny. Was the expansion slowing down due to gravity, and if so, by how much? Would it slow enough to eventually halt and recollapse, a closed universe, or continue forever, an open or flat universe. Measuring the expansion rate, the Hubble constant, and how it changed over time became a primary goal of observational cosmology, as the answer held clues to the universe's total mass-energy density and its ultimate fate. While the discovery of accelerating expansion would come much later, the immediate consequence of discovering expansion at all was the framing of these fundamental questions about the universe's past, present, and future trajectory. The confirmation of galaxies, comparable to or larger than the Milky Way, also had immediate consequences for understanding galactic structure and formation mechanisms. If galaxies came in such diverse types, what physical processes were responsible? The stark differences between gas-rich star-forming spirals and gas-poor, quiescent ellipticals demanded explanation. This spurred theoretical work on stellar evolution within galaxies, chemical enrichment processes, the role of angular momentum in shaping disks, and, crucially, the importance of galaxy interactions and mergers. The realization that galaxies were not isolated islands, but often resided in groups and clusters, where collisions would be inevitable over cosmic time, provided a natural mechanism for transforming spirals into ellipticals and building up the most massive systems. The consequence was a shift towards viewing galaxies not as static objects, but as dynamic ecosystems interacting with their environment and evolving through mergers. This focus on interactions naturally led to the need to understand the role of environment more broadly. Why were ellipticals found predominantly in clusters, while spirals favored the field? The immediate consequence was the development of theories like RAM pressure stripping and galaxy harassment, proposing physical mechanisms by which the dense cluster environment could directly alter the morphology and star formation activity of infalling galaxies. Studying galaxy populations as a function of environment became a key investigative strategy. Finally, the realization of the universe's vast scale and age had an immediate, though perhaps less tangible, philosophical consequence. It cemented the Copernican principle on a grand scale, the idea that we do not occupy a privileged or central position in the cosmos. Not only is Earth not the center and the Sun not the center, but our entire Milky Way galaxy is just one typical example among trillions. Situated in no particularly special location, within an expanding universe that appears statistically the same in all directions, isotropic and homogeneous on large scales. This cosmic democratization, this loss of centrality, was a profound intellectual and emotional adjustment, forcing a re-evaluation of humanity's significance in the grand scheme. The immediate consequence was a deep sense of humility, mixed with an exhilarating sense of the universe's boundless possibilities. In essence, the turning point triggered by Hubble's discoveries acted like a breaking dam. The immediate consequence was a flood of new questions, new research directions, new technological demands, and a fundamental reshaping of our entire cosmological worldview. Extragalactic astronomy was born, look-back time became a tool, cosmic expansion became the defining narrative, galaxy evolution became a central field of study, the drive for larger telescopes intensified, and humanity's perception of its own place shifted irrevocably. The quiet work of measuring flickering stars in a faint nebula had unleashed a cascade of consequences that continue to propel scientific exploration and shape our understanding of the universe to this day. The consequences of the great turning point, that dual revelation of extragalactic scale and cosmic expansion delivered in the 1920s, were immediate and revolutionary, fundamentally reshaping the landscape of astronomy and cosmology. New fields of inquiry were born, new technologies spurred, and a dynamic, evolutionary narrative replaced the static cosmos of antiquity. But the impact of this profound shift extended far beyond the scientific community. Like the slow, deep resonance of a struck bell, its echoes traveled through time, subtly yet profoundly altering human culture, our technological capabilities, our understanding of history, and ultimately our perception of what it means to exist within this immense, unfolding cosmic story. Perhaps the most immediate and visceral impact, the echo that resonated most deeply within the collective human psyche, arrived not through complex equations or faint spectral lines, but through images. Specifically, it was the images of our own planet, Earth, captured from space during the Apollo lunar missions in the late 1960s and early 1970s, that crystallized the emotional weight of the new cosmology. While these photographs were focused inward, looking back toward home rather than outward toward distant galaxies, their power derived precisely from the vast, newly revealed cosmic context within which they were taken. Decades earlier, science had intellectually dismantled our sense of centrality, revealing the Milky Way as just one galaxy among trillions. Now, the photographs from the moon provided the stark, visual, emotional counterpart to that intellectual realization. Images like Earthrise, showing our vibrant blue and white marble suspended above the barren grey lunar horizon, and the iconic blue marble photograph, depicting the full, sunlit Earth hanging alone in the absolute blackness of space, conveyed a message words could barely touch. For the first time in history, humanity saw its home not as the stable ground beneath its feet, not as a flat map divided by borders, but as a single, finite, visibly fragile sphere adrift in an infinite void. The astronauts themselves, the privileged few who witnessed this view firsthand, consistently reported experiencing a profound cognitive shift, often termed the overview effect, a sudden, overwhelming sense of the planet's interconnectedness, its beauty, its apparent vulnerability, and the arbitrariness of the political divisions that seemed so significant from the surface. From lunar distance, Earth appeared as a unified system, a single oasis of life in an otherwise desolate expanse. This perspective, powerfully communicated through the widespread dissemination of those photographs, resonated deeply across global culture. The image of the blue marble quickly became an emblem, an icon, for the burgeoning environmental movement of the 1970s. It provided a potent visual argument for global cooperation, for the need to protect our shared atmosphere, oceans, and biosphere. It fostered a sense, perhaps for the first time on a mass scale, that humanity was fundamentally interconnected, sharing a single, finite island in the vast cosmic ocean. The impact echoed through art, philosophy, and social consciousness, subtly reinforcing the sense that individual lives and local concerns were inextricably linked to the fate of the planet as a whole. A planet whose preciousness and isolation were now starkly visible against the backdrop of the immense, impersonal cosmos revealed by extragalactic astronomy. Seeing Earth from the outside mirrored the intellectual leap of seeing the Milky Way from the outside. Both were acts of perspective that fostered both humility and a sense of shared belonging. Beyond these profound cultural and philosophical shifts, the relentless drive to understand this newly revealed universe of galaxies had tangible technological impacts that echoed back, often unexpectedly, into daily life on Earth. The very act of observing these incredibly faint, distant objects, of measuring their properties across billions of light years, pushed the boundaries of engineering, materials science, and computation to their limits. The need to capture the feeble light from the edge of the observable universe spurred the development of larger telescopes, necessitating innovations in mirrorcasting, polishing techniques, complex support structures to prevent sagging, and sophisticated pointing and tracking systems. Techniques like adaptive optics, developed to compensate for the blurring effects of Earth's atmosphere by using deformable mirrors adjusted hundreds of times per second based on laser-guide stars, allowed ground-based telescopes to achieve image sharpness previously possible only from space, dramatically enhancing our ability to study distant galaxies. Perhaps most pervasively, The challenge of detecting incredibly faint signals drove the development of highly sensitive electronic detectors. The transition from relying on the limited sensitivity and nonlinearity of photographic plates to the high quantum efficiency and digital nature of charge-coupled devices, CCDs, in the 1970s and 80s, revolutionized observational astronomy. CCDs, initially developed partly for astronomical applications, became the core technology behind digital cameras, video recorders, medical imaging systems, and countless other devices that are now ubiquitous in modern life. The pursuit of ancient starlight directly contributed to the digital imaging revolution. Furthermore, the sheer volume and complexity of data generated by large-scale galactic surveys, mapping the positions, redshifts, shapes, colors, and spectra of millions, even billions, of galaxies, necessitated significant advances in data storage, high-speed networking, image processing algorithms, and statistical analysis techniques. Methods developed within astronomy for handling big data, performing automated classifications, searching for faint patterns, and managing complex databases often found applications in other scientific disciplines, finance, and information technology. The echoes of mapping the cosmos reverberated through the burgeoning digital age. Even the fundamental physics uncovered through studying the cosmos on its grandest scales found practical terrestrial applications. Einstein's theories of special and general relativity, initially developed to understand gravity, space-time, and the behavior of light, and later confirmed through astronomical observations like the bending of starlight and the expansion of the universe, became essential components of modern technology. The most prominent example is the Global Positioning System, GPS. The system relies on a constellation of satellites orbiting Earth, each carrying highly precise atomic clocks. To achieve the required navigational accuracy, the GPS system must constantly account for relativistic effects predicted by Einstein's theories. Due to their high orbital speeds relative to ground observers, the satellite clocks run slightly slower, time dilation due to special relativity. Simultaneously, because they are in a weaker gravitational field farther from Earth's center, their clocks run slightly faster, gravitational time dilation due to general relativity. The latter effect is larger, resulting in a net gain. If these combined relativistic corrections were not applied, the timing signals would drift significantly, and the calculated positions on Earth would accumulate errors of several kilometers per day, rendering the entire system useless. Every time we rely on GPS to navigate, we are implicitly using the echoes of theories developed to comprehend the structure and dynamics of the entire universe. The investigation into the grandest scales reverberated back to guide us accurately on our smallest, most personal journeys. But perhaps the most profound and deeply personal impact, the echo that connects our individual existence most directly to the vast cosmic story revealed by the discovery of galaxies, lies in how this new understanding rewrote the narrative of our own material origins. The key realization, solidified in the mid-20th century through the work of physicists like Fred Hoyle, Willie Fowler, and Margaret and Geoffrey Burbidge, was stellar nucleosynthesis. This theory, supported by overwhelming observational evidence from stellar spectroscopy and meteorite analysis, demonstrated conclusively that the chemical elements heavier than hydrogen, helium, and trace amounts of lithium, which were formed in the Big Bang itself, were not primordial. Instead, they were forged inside stars through nuclear fusion processes during their lifetimes and, particularly for the heaviest elements, in the cataclysmic explosions of massive stars supernovae at the ends of their lives. Galaxies, as the primary hosts of stars, are therefore the cosmic crucibles where this elemental creation takes place on a grand scale. As successive generations of stars are born, live, and die within a galaxy like the Milky Way, They gradually enrich the interstellar medium. The diffuse gas and dust clouds residing between the stars with these newly synthesized heavier elements, often referred to collectively by astronomers as metals. Subsequent generations of stars then form from this chemically enriched material, incorporating these heavier elements into their own composition and, crucially, into the protoplanetary disks from which planets like Earth eventually coalesce. The consequence of understanding this process of galactic chemical evolution was monumental. It explained, for the first time, the very substance of our world and, indeed, ourselves. The silicon and oxygen that make up the rocks beneath our feet, the nitrogen and oxygen composing the air we breathe, the carbon forming the versatile backbone of all organic molecules essential for life, the iron core of our planet generating its protective magnetic field, the iron in the hemoglobin carrying oxygen through our bloodstreams, all these elements, vital for the existence of Earth and life as we know it, were created inside previous generations of stars, ejected into the Milky Way's interstellar medium over billions of years, and finally gathered together in the collapsing cloud of gas and dust that formed our Sun and solar system approximately 4.6 billion years ago. The poetic phrase, "we are stardust," was thus transformed into a profound, literal, scientific truth. Our individual existence, the very atoms composing our bodies, became a direct echo, a tangible legacy of the galaxy's long, slow history of stellar birth, nuclear fusion, and explosive death. Comparing the detailed chemical abundances measured in our Sun and solar system, for example, from meteorites to those observed in stars of different ages or in different regions of the galaxy, like the metal-poor halo versus the metal-rich disk, became a powerful tool for tracing our own cosmic lineage, for understanding the specific sequence of enrichment events that led to the particular chemical mix necessary for the formation of a rocky planet like Earth and the emergence of carbon-based life. Our personal, biological story was revealed to be inseparable from the galaxy's collective chemical biography. This connection deepened further with the development of the concept of the Galactic Habitable Zone, GHZ. Recognizing that conditions necessary for complex life might vary significantly across the vast expanse of the galaxy, scientists proposed that certain regions might be more conducive to life's development and long-term persistence than others. This zone is typically envisioned as an annular region within the galactic disk, defined by competing factors. Closer to the galactic center, the density of stars is much higher, increasing the risk of lethal radiation from nearby supernovae, close stellar encounters that could disrupt planetary orbits, or gamma-ray bursts. Furthermore, the central regions are often richer in heavy elements, which might seem beneficial, but excessively high metallicity could potentially hinder the formation of stable planetary systems. Conversely, farther out in the galactic disk or in the halo, stars tend to be older and significantly less enriched in heavy elements, metals. Without a sufficient abundance of elements like silicon, iron, magnesium, etc., it becomes difficult, perhaps impossible, to form substantial rocky planets like Earth. Systems in these metal-poor regions might be dominated by gas giants or consist only of primordial hydrogen and helium. The GHZ represents the proposed sweet spot in between a region, encompassing our own solar system's location around 25 to 30,000 light-years from the center, where there is a sufficient abundance of heavy elements to form rocky planets, but where the stellar density is low enough, the distance from the violent galactic core is great enough, and the rate of catastrophic events like supernovae is infrequent enough to provide a relatively stable, quiescent environment conducive to the evolution of complex life over billions of years. The consequence of this theory was a further refinement of our cosmic address, suggesting that our existence might depend not just on the properties of our star and planet, but also on our fortunate location within a potentially favored neighborhood of the galaxy. Our presence became an echo not just of stellar history, but of galactic structure, chemical gradients, and environmental stability. The impact of understanding galactic dynamics also extended our historical perspective forward into the distant future. The knowledge, derived from precise measurements of galactic motions, that the Milky Way and the Andromeda Galaxy are gravitationally bound and inevitably heading for a colossal merger in about 4 to 5 billion years, provides a scientifically grounded, albeit mind-bogglingly distant, glimpse into the ultimate fate of our cosmic home. While this timescale vastly exceeds the current lifespan of humanity, it serves as a powerful reminder that even structures as immense and seemingly permanent as galaxies are not eternal. They evolve, they interact, they transform. Our individual lives, the future history of life on Earth should it survive the sun's own evolution, and the entire trajectory of our civilization unfold against this backdrop of slow but inexorable galactic change. We are passengers on a galactic ship whose long-term course, involving a majestic but transformative collision, is already set by the unyielding laws of gravity. This long-term perspective, born directly from studying the motions and interactions of galaxies, connects our present moment to a future far beyond our immediate concerns, embedding our local story within the galaxy's own ultimate, evolving destiny. Finally, the sheer scale and age of the universe revealed by the discovery of galaxies and the subsequent mapping of cosmic expansion back towards the Big Bang had a profound philosophical impact, forcing a direct confrontation with the concept of deep time. The universe was not mere thousands, but billions of years old. Galaxies formed, evolved, collided, and faded over timescales that dwarf human history and comprehension. Our own existence, as individuals and even as a species, was revealed to be an astonishingly fleeting moment, a brief flicker of awareness within this immense sweep of cosmic history. Did this vastness render human existence insignificant? For some, perhaps, fostering a sense of cosmic vertigo or existential angst. But for others, the response, the echo felt across time, was different. Recognizing our place within this ancient, ongoing and lawful story could also foster a sense of profound connection and even purpose. If the universe, through 13.8 billion years of galactic formation, stellar evolution, and chemical enrichment, had ultimately produced the conditions necessary for consciousness to arise, then perhaps our role, however temporary, was precisely to be the part of the universe that could witness, measure, understand, and perhaps even appreciate the rest. The brief spark of human awareness became, in this view, not an insignificant cosmic accident, but the universe's own emergent way of reflecting upon itself. Our individual search for meaning, our collective scientific quest, became intertwined with the cosmos's own unfolding narrative, written in starlight across the vast expanse of deep time. In summary, the impact of discovering the true nature and scale of galaxies echoed far beyond. We have journeyed through immense structures of light and shadow, comparing our familiar Milky Way to the colossal giants that anchor the cosmic web. We have traced the arc of discovery, from the first unsettling hints that our galaxy was not alone to the profound revelations of an expanding universe dominated by unseen dark matter and accelerating dark energy. We have felt the consequences of these discoveries ripple through science and culture, reshaping our technology, our understanding of origins, and our very sense of place within deep time. But woven through this grand narrative of cosmic forces and staggering scales is another, quieter, yet perhaps more fundamental story. It is the story of the human element. It is the refocusing from the immense objects of study back to the small, fragile, yet relentlessly curious beings who undertook the journey of understanding. Behind every equation, every telescopic observation, every paradigm shift lies the human mind, driven by an ancient innate longing to explore, to comprehend, and to find meaning in the vastness that surrounds us. This chapter returns to them, to the dreamers, the meticulous observers, the forgotten figures whose individual efforts, often carried out in quiet isolation or against prevailing skepticism, collectively forged the path to our current cosmic awareness. For all our sophisticated technology, the quest to understand the universe begins not with machines, but with imagination. It begins with the simple, primal act of looking up and wondering. This impulse, this need to see what lies beyond the horizon, is perhaps one of the defining characteristics of our species. Long before we built telescopes, long before we even understood the nature of stars, ancient cultures mapped the heavens, wove constellations into mythologies, and sought patterns in the celestial dance. This wasn't merely practical navigation. It was an expression of a deeper need to connect, to feel a sense of belonging within a cosmos that seemed both infinitely vast and intimately present. The story of discovering galaxies, then, has its roots in these early dreamers, but the specific intellectual lineage that led to our modern understanding often traces back to figures who dared to push the boundaries of accepted thought, even without definitive proof. Immanuel Kant, the 18th century philosopher, contemplating the nature of the fuzzy nebulae seen through early telescopes, speculated with remarkable prescience that some might be island universes, entire galaxies, like our own Milky Way, lying at immense distances. His reasoning was philosophical, grounded in the idea of an infinite or near-infinite creation. But his intuition planted a seed that would take nearly 2 centuries to fully bloom observationally. He was one of the first dreamers to truly conceptualize a universe populated by galaxies. The path from philosophical dream to scientific measurement, however, required meticulous, often thankless, observational work. It required figures like Henrietta Leavitt, working in the early 1900s at the Harvard College Observatory. At a time when women were largely excluded from leading roles in science, Leavitt served as a human computer, painstakingly analyzing photographic plates, capturing the light from stars in the nearby Magellanic Clouds. It was through this meticulous, repetitive task that she discovered the crucial period-luminosity relationship for Cepheid variable stars. She noticed that the brighter Cepheids took longer to complete their pulsation cycles. This seemingly simple correlation was, in fact, the key that would unlock cosmic distances. Leavitt provided the essential tool, the standard candle, though she herself might not have fully grasped the revolutionary implications her discovery would soon have for mapping the entire universe. Her quiet, dedicated work, often overlooked in popular histories, formed the bedrock upon which Hubble's later discoveries would stand. Simultaneously, another crucial piece of the puzzle was being gathered, though its significance was also not immediately understood. Vesto Slipher, working at the Lowell Observatory in Arizona from 1912 onwards, undertook the arduous task of measuring the spectra of the faint spiral nebulae. Using long photographic exposures spread over many nights, he managed to capture enough light to analyze its properties. He expected to find random motions, some nebulae moving towards us, some away, reflecting their movement within the Milky Way. Instead, he found something deeply perplexing. The vast majority of the spiral nebulae he observed showed significant redshifts. Their spectral lines were systematically shifted towards longer, redder wavelengths, indicating they were moving away from us, often at astonishing speeds, hundreds or even thousands of kilometers per second. Slipher himself was puzzled by this result, this apparent great galactic exodus. He meticulously documented the data, presenting it to his colleagues, but its true meaning remained elusive until placed within the larger context provided by distance measurements. Slipher, the careful observer, had uncovered a fundamental property of the universe, its expansion even before the universe's true scale was known. Then came Edwin Hubble, the figure most famously associated with the discovery of galaxies and cosmic expansion. Hubble possessed a unique combination of observational skill, theoretical insight, building upon the work of Leavitt and Slipher, access to the world's most powerful telescope at the time, the 100-inch Hooker telescope at Mount Wilson, and perhaps a touch of good fortune. His relentless pursuit of Cepheid variables within the Andromeda Nebula, culminating in the irrefutable calculation of its immense distance in 1924, was the watershed moment. But Hubble's contribution didn't stop there. Recognizing the importance of Slipher's redshift data, he, along with his assistant Milton Humason, extended these measurements to fainter, more distant galaxies. By combining his own distance estimates, derived from Cepheids and other indicators, with these redshift measurements, he uncovered the systematic relationship now known as Hubble's law. Recession velocity is proportional to distance. Hubble not only proved the existence of other galaxies, but also provided the first observational evidence for the expansion of the entire universe, laying the foundation for modern cosmology. He was the synthesizer, the observer who connected the crucial dots others had painstakingly gathered. Yet, even as the grand picture began to emerge, anomalies persisted, pointing towards deeper mysteries. Fritz Zwicky, a brilliant but often controversial astronomer working at Caltech in the 1930s, turned his attention to galaxy clusters, particularly the dense Coma cluster, studying the motions of individual galaxies orbiting within the cluster. Zwicky realized they were moving far too fast. The visible mass of all the stars in the cluster's galaxies, calculated based on their light, exerted far too little gravity to hold these rapidly moving galaxies captive. The cluster should be flying apart. To explain this discrepancy, Zwicky proposed the existence of unseen, non-luminous matter, dunkel materie, or dark matter, pervading the cluster, providing the necessary additional gravitational glue. His calculations suggested this dark matter might outweigh the visible matter by a significant factor. Zwicky's idea was largely ignored or met with skepticism by the astronomical community for decades, partly due to his abrasive personality and partly because the evidence, while suggestive, it wasn't yet overwhelming. He was a dreamer ahead of his time, glimpsing the invisible universe long before the tools existed to map it convincingly. It wasn't until the 1970s that the dark matter mystery resurfaced with undeniable force, thanks largely to the meticulous work of Vera Rubin and her colleague Kent Ford. Rubin, another pioneering woman in a field dominated by men, chose to focus on a seemingly straightforward problem, measuring the rotation curves of spiral galaxies, mapping how orbital speeds varied with distance from the galactic center. Using sensitive spectrographs, she observed the Doppler shifts of gas clouds and stars at various radii in galaxies like Andromeda. Like Zwicky, she expected to find speeds decreasing at larger distances, following Kepler's laws, as the influence of the central visible mass diminished. Instead, she consistently found that the rotation curves remained remarkably flat. Stars and gas in the outer fainter regions were orbiting just as fast as those closer in. Rubin's careful, systematic observations provided compelling, irrefutable evidence that spiral galaxies, including our own Milky Way, must be embedded within vast, massive halos of invisible dark matter, extending far beyond their luminous boundaries. Her work transformed Zwicky's speculative idea into a central pillar of modern astrophysics. Rubin, the persistent investigator, patiently gathered the data that forced the scientific community to confront the reality that most of the universe's matter is hidden from view. These figures, Kant, the philosophical visionary, Leavitt, the meticulous data analyst, Slipher, the careful, spectroscopic observer, Hubble, the synthesizer and discoverer of scale, Zwicky, the iconoclastic theorist glimpsing the invisible, Rubin, the tenacious investigator, confirming its presence, represent just a few threads in the rich human tapestry of this scientific journey. Countless other astronomers, physicists, engineers, technicians, and even amateur observers contributed vital pieces along the way, often working anonymously, driven by that same fundamental curiosity. The human element is also present in the very act of observation itself, especially in the early days. Before automated telescopes and digital detectors, astronomy demanded incredible patience and dedication. Imagine spending night after freezing night at a remote mountain observatory, guiding a telescope by hand to keep a faint smudge of light perfectly centered on a photographic plate for hours, developing those plates in darkrooms, and then spending days or weeks meticulously measuring tiny positions or subtle shifts in spectral lines. It was a labor of love, an act of faith in the scientific process, often yielding results only after years of effort. This human element extends beyond individual efforts to the collaborative and sometimes competitive nature of science itself. Discoveries are rarely made in isolation. They build upon previous work, are tested and challenged by colleagues, refined through debate, and ultimately integrated into a shared understanding. The great debate between Shapley and Curtis, while ultimately resolved by Hubble's data, was a crucial part of the process, sharpening the questions and highlighting the evidence needed. The decades-long skepticism surrounding dark matter spurred researchers to gather more and better data, ultimately strengthening the case. Science progresses through this collective, self-correcting dialogue, a human conversation played out across generations. And underpinning it all is that fundamental human drive, that restlessness Tsiolkovsky identified. The need to move beyond the cradle, to explore, to understand our context. Even if we cannot physically travel to distant galaxies, the act of observing them, of measuring their light, of reconstructing their histories, is a form of exploration. Our minds travel where our bodies cannot. The vast distances and timescales revealed by cosmology do not necessarily diminish us. They expand the arena of our understanding. The dreamers are not just those who look up, but those who translate that upward gaze into knowledge, building bridges of comprehension across the cosmic gulfs. The human element is the engine of curiosity that powers the entire scientific enterprise, turning faint flickers of ancient light into a profound, shared story of origins, evolution, and connection. We have journeyed alongside the dreamers and the meticulous observers, the human element that dared to confront the vastness revealed beyond our Milky Way. We have seen how figures like Leavitt provided the keys, how Slipher detected the motion, how Hubble unlocked the scale and expansion, how Zwicky glimpsed the unseen, and how Rubin confirmed its pervasive gravitational reign. Through their collective efforts, spanning generations, a new cosmology emerged. A universe born from a Big Bang, expanding and cooling, its structure sculpted hierarchically by the gravity of dominant dark matter, forming a cosmic web populated by trillions of evolving galaxies, from average spirals like ours to colossal giants forged in the fires of ancient mergers. This picture, assembled from countless clues and fragments of data gathered across billions of light-years, feels coherent, comprehensive, almost complete. It seems we have, after centuries of striving, finally grasped the fundamental architecture of existence, our place within it secured, our comparison between the Milky Way and the giants understood within a robust evolutionary context. The battle for truth, it might seem, has largely been won, but here, precisely at this point of apparent clarity, we encounter the true, enduring opposition. It is not the opposition of outdated ideas stubbornly held, nor the skepticism of those unwilling to accept the evidence. It is a far more profound, more fundamental form of resistance. It is the opposition presented by the universe itself, the quiet, persistent refusal of reality to yield its deepest secrets easily. It is the battle for truth waged not against past ignorance, but against the towering walls of present unknowns, the vast domains where our sophisticated models meet the stark reality of their own incompleteness. The primary front in this ongoing battle concerns the very substance that, as we discovered, dominates the entire cosmic structure: dark matter. Our models require it. The flat rotation curves of spiral galaxies make no sense without it. The confinement of hot gas in galaxy clusters demands its immense gravitational influence. The patterns of gravitational lensing observed around massive structures directly trace its distribution. The intricate structure of the cosmic microwave background, the afterglow of the Big Bang, precisely measures its overall abundance relative to normal matter. The success of cosmological simulations in reproducing the observed large-scale structure depends crucially on the assumption that dark matter is cold, slow-moving, and interacts primarily through gravity. The evidence for dark matter's existence, inferred through its gravitational effects, is overwhelming, drawn from multiple independent lines of inquiry across vastly different scales. Science accepts its reality with high confidence, but the profound opposition, the wall against which decades of intense investigation have repeatedly struck, lies in understanding its nature. What is this invisible substance that constitutes roughly 85% of all matter in the universe? Here, the battle for truth becomes a frustrating siege against silence. We know, with reasonable certainty, what dark matter isn't. It cannot be made of ordinary baryonic matter, protons, neutrons, electrons, simply hiding in dark forms like faint stars, brown dwarfs, cold gas clouds, or isolated black holes. The successful predictions of Big Bang nucleosynthesis, which accurately calculate the primordial abundances of light elements like helium and deuterium based on the measured density of baryons from the CMB, leave no room for such a large amount of additional normal matter. Furthermore, gravitational microlensing surveys searching for massive compact halo objects, MACHOs, have ruled out stellar remnants or brown dwarfs as the primary component. Dark matter must be something fundamentally different, something non-baryonic, something exotic lying beyond the familiar particles of the standard model of particle physics. The leading theoretical candidates fall broadly into categories like WIMPs, weakly interacting massive particles. These are hypothetical particles, perhaps born in the thermal soup of the very early universe, that interact with normal matter only through gravity and the weak nuclear force, hence weakly interacting. Their predicted properties could naturally explain the observed abundance of dark matter. Motivated by this possibility, physicists have mounted an enormous experimental effort to detect WIMPs directly. Vast, ultra-sensitive detectors have been built deep underground in mines or mountain tunnels, shielded from confusing cosmic rays, hoping to catch the incredibly rare signal of a WIMP occasionally bumping into an atomic nucleus within the detector material, causing a tiny flash of light or vibration. Experiments like LUX, Xenon, Panda-X, and others have pushed the limits of sensitivity ever lower. Yet, after decades of searching, no definitive, undisputed WIMP signal has been found. The silence from the underground labs is deafening. Other experiments search for indirect detection signals. If dark matter particles are their own antiparticles, they could annihilate each other when they collide in dense regions like the center of the Milky Way or the hearts of dwarf galaxies, producing secondary particles like gamma rays, neutrinos, or antimatter particles positrons, antiprotons, that could potentially be detected by space-based telescopes like Fermi or AMS, or neutrino observatories like IceCube. Intriguing hints and anomalies have occasionally surfaced, but none have yet provided a smoking gun signature unambiguously attributable to dark matter annihilation. Particle accelerators like the Large Hadron Collider, LHC, also join the hunt, attempting to create dark matter particles directly in high-energy proton collisions. If dark matter particles are produced, they would escape the detector, unseen, being weakly interacting. But their presence could be inferred from missing energy and momentum in the collision debris. Again, despite extensive searches pushing into new energy frontiers, the LHC has yet to find conclusive evidence for physics beyond the standard model that could account for dark matter. The opposition here is profound. Our cosmological model relies utterly on the existence of dark matter, yet its fundamental nature remains a complete blank. Decades of dedicated, ingenious, and expensive experiments designed to detect the leading candidates have yielded null results. This persistent lack of detection constitutes a major crisis, or at least a significant tension, in fundamental physics and cosmology. Are the WIMP models simply wrong? Is dark matter composed of something even more elusive, like axions, extremely light, hypothetical particles? Does it interact even more weakly than assumed? Or could the evidence we attribute to dark matter point towards something even more radical, like a breakdown of our understanding of gravity itself on galactic scales, as proposed by theories like modified Newtonian dynamics, or MOND? Though these face their own significant challenges in explaining all observations, particularly on cluster scales and in the CMB, the battle for truth continues, with researchers pursuing multiple theoretical avenues and experimental strategies, pushing against the resistance of the unknown. The universe guards the secret of its dominant matter component closely. If the mystery of dark matter forms one flank of the opposition, the enigma of dark energy forms the other, perhaps even more formidable front. As discussed, the discovery in the late 1990s that the expansion of the universe is not slowing down due to gravity, but is instead accelerating, was a bombshell. It implied the existence of some pervasive entity or property of space-time itself, possessing a negative pressure, acting repulsively on cosmic scales, and constituting nearly 70% of the universe's total energy density. The opposition here is, if anything, even deeper than for dark matter. While dark matter at least behaves gravitationally like matter, albeit invisible, dark energy seems to behave like nothing familiar at all. Its existence is inferred solely from its effect on the cosmic expansion history, primarily through the dimming of distant supernovae and its imprint on the large-scale structure and the CMB. But its fundamental nature remains completely baffling. Is dark energy the cosmological constant, La, that Einstein initially proposed and later retracted? This would imply that empty space itself possesses a small, non-zero, intrinsic energy density, constant throughout space and time, whose negative pressure drives acceleration. This possibility is consistent with current observational data, forming the basis of the standard LCDM, lambda, cold dark matter, cosmological model. However, theoretical attempts to calculate the expected value of this vacuum energy from quantum field theory yield results that are staggeringly, absurdly larger, by some 120 orders of magnitude, than the tiny value observed cosmologically. This cosmological constant problem represents perhaps the most profound mismatch between theory and observation in all of physics, a stark contradiction suggesting a deep flaw in our fundamental understanding. Alternatively, is dark energy something dynamic, a quintessence field whose energy density changes slowly over cosmic time? Or could the observed acceleration indicate that Einstein's theory of general relativity itself breaks down on cosmic scales, requiring modification? Minds divide fiercely among these possibilities, with theorists exploring numerous speculative models, while observers strive to make ever more precise measurements of the expansion history, for example, using baryon acoustic oscillations, weak lensing surveys, or galaxy cluster counts, hoping to find subtle deviations from a simple cosmological constant that might hint at the true nature of this dominant, repulsive force. The battle for truth against the mystery of dark energy is a battle fought at the very edge of fundamental physics. It represents a profound opposition from the universe, challenging our most basic understanding of space, time, gravity, and quantum mechanics. The fact that 95% of the universe's energy density, dark matter plus dark energy, resides in forms whose nature we do not comprehend is a humbling testament to the scale of our remaining ignorance. Beyond these fundamental unknowns about cosmic composition, the opposition also manifests in observational challenges and tensions. While the overall LCDM model provides an excellent fit to a vast range of data, tensions persist. For example, there is currently a statistically significant discrepancy, the Hubble tension, between the value of the Hubble constant, the current expansion rate, measured locally using standard candles like Cepheids and supernovae, and the value inferred from observations of the early universe via the cosmic microwave background, assuming the standard LCDM model. Does this tension signal unaccounted for systematic errors in one or both types of measurement, or could it be the first hint of new physics beyond the standard model, perhaps involving exotic forms of dark energy or modifications to gravity? The battle for truth here plays out in the meticulous analysis of data, the careful scrutiny of potential errors, and the theoretical exploration of new possibilities. Furthermore, even within the standard model, precisely modeling the complex gastrophysics, the messy details of gas cooling, star formation, supernova feedback, black hole accretion, and outflows that govern the visible evolution of galaxies within their dark matter halos remains incredibly challenging. Cosmological simulations have become remarkably sophisticated, yet they still rely on subgrid recipes to approximate these complex processes, leading to uncertainties and ongoing debate about how accurately they capture reality, particularly for phenomena like the quenching of star formation in massive galaxies or the properties of faint dwarf galaxies. The opposition here is the sheer complexity of baryonic physics interacting with the large-scale structure. The battle for truth, therefore, is far from over. While the broad picture of an expanding universe dominated by dark matter and dark energy, within which galaxies form hierarchically, seems secure, fundamental questions about the nature of these dominant components remain wide open. Tensions persist in the observational data, hinting at potential cracks in the standard model, and the intricate details of galaxy evolution continue to challenge theorists and simulators. The opposition is not just a lack of data, but often a lack of fundamental understanding, a confrontation with the limits of current physical theories. Science progresses by pushing against this resistance, by acknowledging the unknowns, by designing new experiments and observations to probe the mysteries, and by constantly questioning and refining its models in the face of contradictory evidence. The comparison between our Milky Way and the cosmic giants is embedded within this ongoing battle, a narrative shaped as much by what we don't know as by what we do. The universe, it seems, still holds its deepest truths in reserve, offering resistance that fuels the very investigation seeking to overcome it. Our cosmic investigation, born from the simple act of comparing our familiar Milky Way to the newly discovered galaxies beyond, has led us on a path of ever-increasing complexity and deepening mystery. We journeyed from the initial shock of realizing our galaxy's profound averageness through the intricate mapping of its structure and our quiet place within it. We retraced the pivotal discovery that shattered our cosmic isolation and witnessed the immediate human response, awe, disbelief, and the drive to classify the bewildering diversity of galactic forms. Yet, contradictions quickly arose, challenging simple evolutionary theories and dividing minds between models of rapid collapse versus gradual, hierarchical growth. The investigation intensified, employing ingenious tools to gather faint clues across billions of light years, only to uncover the pervasive, gravitational dominance of unseen dark matter, and the accelerating expansion driven by enigmatic dark energy. We confronted the opposition, the stark reality that 95% of the universe remains fundamentally unknown, a battle for truth waged against the very limits of our current understanding. It feels as though we have reached an impasse, a point where the accumulation of knowledge has paradoxically led to a greater awareness of our ignorance. The map is filled with vast territories labelled terra incognita. The giants like IC 1101 stand as monuments to processes governed by forces we cannot directly perceive. The comparison seems almost stalled, framed by fundamental unknowns. But it is precisely here, in this place of confronting limits, that a different kind of shift can occur. It is not the discovery of a new particle or the mapping of a new structure. It is something quieter, more internal, yet potentially far more transformative. It is an awakening. It is the transition from merely accumulating knowledge, facts, figures, classifications, theories, to grasping wisdom. It is a new awareness, a change not in what we see, but in how we see everything we have already learned. It is the universe, perhaps, beginning to understand itself through us in a different way. The first part of this awakening involves revisiting our initial hook, our galaxy's averageness, and finding not disappointment or insignificance, but profound meaning. Yes, the Milky Way is not the largest, not the brightest, not the most massive galaxy in the cosmos. It sits comfortably in the middle ground, but the wisdom emerging from decades of study suggests this very mediocrity might be its greatest virtue, the key to its, and our, existence. Consider the alternatives revealed by our investigation. The colossal giant elliptical galaxies, often born from violent, repeated mergers in the chaotic cores of dense galaxy clusters, are ancient and largely quiescent. Their star formations ceased billions of years ago, their environments perhaps too harsh, too irradiated, too dynamically unstable for the long, slow, uninterrupted evolution that complex life seems to require. At the other extreme, tiny dwarf galaxies, while numerous, may lack sufficient heavy elements, forged in earlier generations of massive stars, to form rocky planets like Earth, or their shallow gravitational wells might make them vulnerable to having their essential gas stripped away by interactions or internal feedback. The awakening is the realization that the Milky Way's average status places it in a kind of cosmic sweet spot. It is massive enough to have retained its gas supply, sustain ongoing star formation for billions of years, and build up a sufficient reservoir of heavy elements needed for terrestrial planets and biochemistry. Yet, it is likely not so massive or situated in such a dense environment that it has undergone the kind of catastrophic merger history that characterizes the giant ellipticals, allowing its relatively stable, thin disk structure to persist. Furthermore, our solar system's location within that disk, in a quiet spur away from the hazardous galactic center and dense spiral arms, adds another layer of fortunate tranquility. The wisdom here is a shift from valuing extremes to valuing balance. Our galaxy's ordinariness is not a sign of insignificance, but potentially a prerequisite for significance. It represents a stable, fertile middle ground where complexity, perhaps including life and consciousness, has had the billions of years of relative peace needed to emerge and evolve. The awakening is appreciating that average might actually be optimal for the kind of intricate, long-term development that led to us. The second part of this awakening involves a shift in how we perceive galaxies themselves, moving beyond seeing them as static objects to be classified and compared, and embracing them as dynamic, evolving ecosystems. We learn the scientific facts. Stars are born from collapsing gas clouds, fuse elements in their cores, and return those elements to the galaxy when they die. This material enriches the interstellar medium, fueling the formation of new stars and planets. The wisdom is internalizing this not just as a process, but as a cycle, a vast, galactic-scale metabolism that connects everything within it across space and time. The awakening is recognizing that the Milky Way is not just a structure containing stars, it is a system defined by the continuous flow of matter and energy through those stars. The gas clouds are reservoirs of potential. The young blue stars are moments of intense transformation. The supernovae are acts of violent dispersal and enrichment. The older red stars are repositories of accumulated history. The planets are condensations of that enriched material, and even the central black hole plays a role, potentially regulating the flow through feedback. Seeing the galaxy this way, as an interconnected, self-sustaining, for a time, ecosystem, changes the comparison. Giant ellipticals are not just bigger, they represent ecosystems that have reached a different stage, perhaps one of senescence, where the cycle of star formation has largely ceased, their internal resources exhausted or expelled. Dwarf galaxies might be ecosystems struggling to retain their vital resources against the gravitational tides of larger neighbors. This ecosystem perspective fosters a new awareness of interconnectedness across scales. The physics governing nuclear fusion within a single star dictates the chemical enrichment of the entire galaxy over billions of years. The gravitational dynamics of dark matter halos shape the environment where gas can cool and form those stars. The large-scale structure of the cosmic web influences the merger rate and gas supply available to individual galaxies. The awakening is seeing the universe not as a collection of separate objects at different sizes, but as a deeply interwoven system where processes at the smallest scales influence the largest structures, and vice versa. Our existence on Earth is a product not just of our planet or our star, but of the entire galactic ecosystem functioning over cosmic time. This leads to a renewed appreciation for the role of time itself. Our comparison of galaxies often feels like comparing static snapshots, but the awakening involves seeing these snapshots as single frames in an incredibly long movie. The differences between a spiral like the Milky Way and a giant elliptical like IC 1101 are not just differences in size, but differences in age and history. IC 1101 reached its colossal state through billions of years of mergers, a process the Milky Way has largely avoided, but will eventually participate in with Andromeda. Understanding galaxies requires thinking not just in 3 spatial dimensions, but in 4, incorporating the immense sweep of cosmic time during which these structures assemble, interact, and evolve. The wisdom is recognizing that change, driven by gravity and the life cycles of stars, is the fundamental constant, and that every structure we see is temporary, a transient form in an ongoing cosmic unfolding. Finally, this awakening brings us back, with new insight, to the profound mysteries of dark matter and dark energy. We acknowledge them as opposition, as vast unknowns. The awakening involves embracing this unknown not as a barrier, but as an integral part of the reality we inhabit. The hidden truth that 95% of the universe is composed of substances we don't understand isn't just a scientific problem to be solved. It is a fundamental characteristic of the cosmos we find ourselves in. The wisdom here is humility, but not a passive resignation. It is an active, engaged humility that recognizes the limits of our current knowledge while simultaneously fueling the drive to push beyond them. It is the awareness that our elegant models, while powerful, are likely incomplete descriptions of a reality far richer and stranger than we currently grasp. Comparing the Milky Way to the giants becomes an exercise not just in cataloguing known properties, but in acknowledging the vast invisible context the dark matter halos. The accelerating expansion that shapes both systems in ways we are still striving to comprehend. The awakening is accepting that mystery is not a sign of failure, but an invitation to deeper inquiry, a fundamental aspect of the universe's dialogue with consciousness. In essence, the awakening is a shift from a perspective focused on objects, classifications, and linear evolution to one centered on processes, interconnections, deep time, and the embracing of fundamental mystery. It involves seeing our average galaxy not as lesser, but as a potentially optimal crucible for complexity. It involves viewing all galaxies as dynamic ecosystems participating in a universal cycle of matter and energy. It requires appreciating the profound influence of the unseen, dark matter, dark energy, environment on the scene. And it fosters a humility that recognizes the limits of our knowledge while celebrating the very capacity to ask the questions. This new awareness doesn't change the data, but it transforms its meaning, allowing us to perceive our place within the cosmos with a richer, deeper, and perhaps ultimately more peaceful understanding. Our quiet drift through the cosmos has brought us face to face with immensity, diversity, and profound mystery. We began with the unsettling hook that our own Milky Way, a structure containing hundreds of billions of stars and spanning 100,000 light-years, is merely average in the grand galactic scheme. We grounded ourselves in the familiar setting of this home galaxy, mapping its spiral arms, its central bar, its dark matter halo. We revisited the spark of discovery, Hubble's pivotal work revealing Andromeda as a distant island universe, shattering our cosmic isolation. The first response was awe and disbelief, followed by the intellectual drive to classify this newfound diversity. Yet, contradictions quickly emerged. The elegant visual sequence of galaxy shapes clashed with the ages of their stars. Theories divided minds. Did galaxies form top-down or bottom-up? The investigation intensified, employing sophisticated tools to gather data across cosmic time, revealing clues but also deepening the enigma, particularly the pervasive presence of unseen dark matter. This led us to the deeper mystery. The hidden truth that the visible universe is largely governed by invisible faith, structures and substances. We confronted the turning point, the dual realization of extragalactic scale and cosmic expansion that birthed modern cosmology. We felt the immediate consequences ripple through science, and the long-term impact echo through culture and our understanding of origins. We honored the human element, the dreamers and observers who paved this path. We faced the stark opposition presented by the universe itself, the stubbornly unknown nature of dark matter and dark energy, the tensions within our models. And finally, we reached an awakening, a new awareness, valuing balance over extremes, seeing galaxies as dynamic ecosystems, and embracing mystery as part of the cosmic condition. Now, after navigating this intricate landscape of discovery and doubt, we arrive at the core. This is the revelation. It is not the unveiling of a single, previously unknown fact that instantly solves all puzzles. Rather, it is the profound, almost breathtaking moment when the myriad threads of evidence, the competing theories, the persistent contradictions, and the overarching mysteries finally weave together into a single, coherent, and powerfully explanatory tapestry. The deepest truth exposed is the emergence of the standard cosmological model, often called lambda cold dark matter or LCDM, incorporating hierarchical structure formation as the unifying framework that successfully explains, at least in broad strokes, the origin, evolution, and observed diversity of galaxies, from average spirals like our Milky Way to the colossal giants like IC 1101. This model, built upon the foundations laid by Einstein's general relativity and the Big Bang theory, and refined over decades through countless observations and simulations, represents the culmination of our investigation. It provides the intellectual climax by resolving many of the key tensions and offering a comprehensive narrative for galactic existence, while simultaneously acknowledging and incorporating the profound mysteries of dark matter and dark energy as essential components of that narrative. The core revelation begins with the primordial universe. According to the standard model, The universe began approximately 13.8 billion years ago in an extremely hot, dense state, the Big Bang. In the very first fractions of a second, tiny quantum fluctuations occurred, creating minuscule variations in density from place to place. These initial ripples, almost imperceptibly small, were the seeds of all future structure. As the universe expanded and cooled, these density fluctuations began to grow, amplified by gravity. Crucially, dark matter played the leading role in this early growth. Because dark matter particles, whatever they may be, do not interact significantly with light or radiation, they were not subject to the intense radiation pressure that kept normal baryonic matter smooth in the early hot universe. Dark matter could therefore begin collapsing gravitationally much earlier, forming the first small, invisible halos or potential wells. Normal matter, composed of hydrogen and helium gas, was initially coupled to the radiation field but eventually decoupled as the universe cooled further around 380,000 years after the Big Bang, when the cosmic microwave background was released. Once decoupled, this baryonic gas was free to fall into the pre-existing gravitational wells carved out by the dark matter halos. This sequence is the first key element of the revelation. Dark matter provides the invisible scaffolding upon which all luminous structure is built. Galaxies do not form in isolation. They form within dark matter halos, accreting gas from their surroundings that cools and condenses at the halo's center. The properties of the halo, its mass, its density profile, its angular momentum, its merger history profoundly influence the properties of the visible galaxy that forms within it. The second key element is the confirmation of hierarchical structure formation as the dominant mechanism. The standard LCDM model predicts, and simulations vividly illustrate, that structure builds bottom up. The first dark matter halos to collapse are relatively small. These small halos then merge gravitationally over cosmic time to form progressively larger and larger halos. As these halos merge, the galaxies residing within them also interact and merge. This continuous process of merging and accretion, driven by gravity acting on dark matter, is the primary engine of galactic growth and evolution throughout cosmic history. The revelation is that galaxies are not static entities formed once, but dynamic structures constantly being assembled and reshaped through this hierarchical process. Within this framework, the puzzling diversity of galaxy morphologies finds a natural explanation. The final shape and type of a galaxy are largely determined by its specific merger history, and the environment shaped by the cosmic web. Spiral galaxies, like our Milky Way, are understood to be the result of relatively quiescent formation histories. They likely formed within dark matter halos that experienced mostly smooth accretion of gas and perhaps numerous minor mergers with much smaller satellite galaxies. These minor interactions add mass gradually, without catastrophically disrupting the fragile, rotating disk of gas and stars. The continuous accretion of cool gas from the surrounding cosmic web or halo allows star formation to persist within the disk for billions of years, maintaining the bright spiral arms. The presence of a central bar, as in our galaxy, can also influence the disk's evolution, potentially funneling gas towards the center and triggering star formation or black hole activity. The revelation is that the elegant structure of a spiral is a sign of a relatively peaceful past, a preserved relic of angular momentum, conservation during formation and subsequent gentle growth. Giant elliptical galaxies, conversely, are revealed as the end products of violent merger histories, particularly major mergers between galaxies of comparable mass. When two large spiral galaxies collide, the intense gravitational forces during the merger effectively destroy their ordered disks. Stars are scattered onto randomized elliptical orbits, forming a large puffy spheroidal structure. The collision triggers dramatic inflows of gas towards the center, fueling intense bursts of star formation. starbursts that rapidly consume much of the available gas reservoir. Feedback from these starbursts, for example, supernova winds, and from the central supermassive black holes, which also grow rapidly during mergers by accreting gas and merging with each other, likely expels much of the remaining gas from the system. The result is a massive, smooth, gas-poor elliptical galaxy dominated by older, redder stars, with little or no ongoing star formation precisely matching the observed properties. The revelation is that the seemingly simple, featureless appearance of giant ellipticals belies a tumultuous past. Their smoothness is the calm after repeated storms. Their colossal size, especially for BCGs like IC1101 residing at cluster centers, is the direct consequence of their privileged position, allowing for continuous hierarchical merging over cosmic time. Lenticular S0 galaxies fit neatly into this picture as likely transitional objects, perhaps spirals that have had their gas supply stripped away by environmental effects like ram pressure in clusters or internal processes, causing star formation to cease but leaving the disk structure largely intact. Irregular galaxies represent systems currently undergoing mergers, tidally disrupted galaxies, or perhaps young galaxies still in the process of initial assembly. The deepest truth, therefore, is this unified evolutionary framework. The diversity of galaxy types is not arbitrary, nor does it represent a simple linear aging sequence. Instead, it reflects different evolutionary pathways dynamically shaped by the interplay of hierarchical merging driven by dark matter gravity, and environmental influences dictated by location within the cosmic web, acting upon the baryonic matter that cools and forms stars within dark matter halos. The apparent contradictions between morphology and stellar populations dissolve within this richer historical context. This framework beautifully explains the morphology-density relation. Clusters are dominated by ellipticals because mergers are frequent and environmental stripping is effective in these dense regions, while spirals thrive in the less crowded field where their disks can survive. It explains the existence of stellar streams and galactic cannibalism as ongoing evidence of hierarchical assembly. It naturally incorporates the coevolution of galaxies and their central black holes through merger-driven accretion and feedback. Crucially, this entire narrative unfolds within the context of the expanding universe governed by dark energy. The expansion itself provides the framework for structure growth, allowing initially small density fluctuations to grow into massive halos over 13.8 billion years. Dark energy, by causing the expansion to accelerate, influences the rate at which structures assemble, potentially slowing down the merger rate in the future and leading to the eventual isolation of bound systems like galaxy clusters. The deepest truth about galaxy evolution is inextricably linked to the deepest truths about the fundamental components and dynamics of the cosmos itself. Applying this revelation to our central comparison provides the climax. The Milky Way's averageness is precisely what the LCDM hierarchical model predicts for a galaxy of its mass forming in a relatively quiescent group environment. Its spiral structure, ongoing star formation, and chemical enrichment history are all consistent with gradual assembly through minor mergers and gas accretion over billions of years within its dominant dark matter halo. It represents a common, stable outcome of cosmic evolution. The colossal scale of giants like IC1101 is also explained as the extreme but natural outcome of the same hierarchical process playing out in the most massive dark matter halos located at the nexus of the cosmic web, the centers of rich galaxy clusters. Their immense size and stellar mass are the result of countless mergers accumulated over cosmic time, fueled by their dominant gravitational position. Their elliptical shape and ancient stellar populations are the inevitable consequences of this violent merger history. They are not a different kind of object fundamentally, but the ultimate expression of hierarchical growth in the most favorable locations. The revelation, therefore, is the power and coherence of the standard cosmological model, LCDM plus hierarchical formation. It is the deepest truth we currently possess about how cosmic structure, from the smallest dwarf galaxies to the largest giants, originates and evolves. It successfully weaves together the Big Bang, dark matter, dark energy, gravity, gas physics, star formation, and feedback into a single, quantitative, and predictive framework that remarkably accounts for the vast diversity of galaxies we observe across cosmic time and space. The contradictions that initially spurred the investigation are largely resolved, or at least contextualized, within this unified picture. This revelation delivers the intellectual climax of our journey. The universe, while still holding deep mysteries regarding the fundamental nature of its dark components, is not an arbitrary collection of objects. It follows understandable physical laws that, acting over billions of years, naturally produce the complex and beautiful tapestry of galaxies we see, including both our familiar home and the awe-inspiring giants that reside in distant cosmic cities. The deepest truth is found not in a single answer, but in the elegant, encompassing, and surprisingly coherent story the universe tells about its own creation. We have arrived, after a long and winding journey through cosmic scales and scientific revolutions, at the revelation. We stand now before the grand tapestry woven by modern cosmology, the standard model known as lambda-cold dark matter, coupled with the understanding of hierarchical structure formation. This framework, born from confronting contradictions and pursuing mysteries, offers a coherent, powerful narrative explaining the universe we observe, from its fiery Big Bang origins to the intricate cosmic web populated by trillions of galaxies. It accounts for the existence of both average spirals like our Milky Way, products of relatively quiet evolution, and colossal giants like IC 1101, forged through eons of mergers in the dense hearts of galaxy clusters. It embraces the profound enigmas of dark matter and dark energy, not as mere problems, but as essential, dominant components of reality itself. We have reached the intellectual climax, the point where the major pieces of the puzzle seem to fall into place, revealing a universe governed by understandable physical laws acting across unimaginable stretches of space and time. Now, after this intense climb towards comprehension, the path invites us to pause. To stand still on this conceptual summit, this is the moment for quiet, for silence, for awe. It is the time to gently step back from the intricate details of the model, from the data points and the equations, from the debates about feedback mechanisms and halo profiles, and simply reflect. What does it all mean? What are the deeper implications of this vast, dynamic, and often invisible universe for our own existence, for our sense of self, for our place within this grand, unfolding story? The first, and perhaps most immediate, reflection returns us to the very substance of our being, grounding the cosmic scale in the intimate reality of our own bodies. The revelation wasn't just about galaxies, it was about the elements forged within them. The understanding of stellar nucleosynthesis, the process by which stars fuse lighter elements into heavier ones and then disperse them through winds and supernovae, fundamentally changed our connection to the cosmos. It revealed that we are not merely in the universe, we are chemically, physically, of the universe. Reflect, for a quiet moment, on the atoms currently composing your body, the carbon that forms the intricate scaffolding of your DNA and proteins, the oxygen that fills your lungs with each breath and combines with hydrogen to form the water vital to your cells, the calcium lending strength to your bones, the iron at the heart of the hemoglobin molecules carrying that oxygen through your bloodstream. None of these essential elements were created on Earth. They weren't even created in our sun. They were painstakingly synthesized, atom by atom, in the unimaginably hot, dense cores of previous generations of massive stars that lived and died within the Milky Way galaxy billions of years before our solar system ever formed. These stellar ancestors, through their life cycles and explosive deaths, seeded the interstellar clouds with the heavy elements necessary for rocky planets and, ultimately, for life itself. The very ground beneath us, the air we breathe, the food we eat, our bodies themselves all are composed of recycled stardust, remnants of ancient cosmic alchemy. The reflection here transcends mere intellectual knowledge. It touches upon a feeling of profound, almost mystical connection. We are not separate observers looking at the stars. The stars are, quite literally, within us. Our physical existence is an echo, a direct legacy of the galaxy's long, slow history of chemical enrichment, of stellar birth and death playing out across millennia. This realization dissolves the perceived boundary between the biological and the astronomical. Life is not something alien imposed upon the cosmos. It is something the cosmos does, given the right ingredients and conditions, using the very materials it forges in its stellar furnaces. We belong here not just by location, but by substance. Flowing from this intimate connection is the reflection on scale and humility. Our journey began by confronting the Milky Way's averageness, its lack of exceptionalism on the cosmic stage. We then encountered the true giants, galaxies like IC 1101, structures so vast they beg a belief. And we glimpsed the scale of the observable universe itself, stretching across 93 billion light-years, containing perhaps 2 trillion galaxies. What does it mean to exist within such immensity? The initial human response might be a feeling of insignificance, a sense of being utterly dwarfed, cosmically irrelevant. Our planet is a tiny speck orbiting an average star in a typical galaxy, lost within an unimaginably vast and ancient whole. Our individual lives, our entire species' history, unfolds on timescales that are vanishingly brief compared to the billions of years of galactic evolution or the lifespan of the universe itself. But the reflection need not end there. Humility does not necessarily equate to insignificance. Recognizing our physical smallness can, paradoxically, lead to a deeper appreciation of our unique position. The vastness doesn't diminish us. It provides the context for our existence. The very laws of physics that operate across these immense scales, gravity assembling structures, nuclear forces forging elements, electromagnetism carrying light across billions of years, are the same laws that operate within our bodies, that allow our sun to shine, that hold our planet together. The awe comes from recognizing this unity of law, this coherence across all scales. The universe is not a chaotic jumble. It is an ordered system, governed by principles that we, despite our smallness, are capable of discovering and comprehending. Our ability to measure the distance to IC 1101, to model the Big Bang, to infer the presence of dark matter, is itself a remarkable testament. It suggests that the human mind, born from the very processes it seeks to understand, is somehow tuned to the logic of the cosmos. This leads to perhaps the most profound reflection of all, the idea that through consciousness, particularly through the scientific endeavor, the universe is becoming aware of itself. For the vast majority of its 13.8 billion year history, the cosmos unfolded in magnificent silence, governed by impersonal laws, producing stars, galaxies, and perhaps even simple life forms, all without self-awareness. Then, on at least one small planet, orbiting one ordinary star in one typical galaxy, configurations of matter arose human brains complex enough to not only exist, but to reflect upon that existence. We build telescopes, instruments designed to gather ancient light. We develop mathematics, a language capable of describing the universe's underlying patterns. We formulate theories, narratives that attempt to explain origins and evolution. In doing so, are we merely observers, detached spectators watching a cosmic play? Or are we something more? Are we the means by which the universe itself achieves self-perception? When we feel awe looking at an image of a distant galaxy, is it just an individual human emotion? Or is it a resonance, a moment where the cosmos, through us, recognizes its own grandeur? This reflection shifts our perceived significance entirely. If consciousness is the universe's way of knowing itself, then our small size and brief lifespan become less important than our capacity for awareness. Our existence, however fragile and localized, contributes something unique to the cosmic story. Meaning, comprehension, perhaps even appreciation. The stardust has not only woken up, it has begun to understand where it came from and the vast structure to which it belongs. This sense of participation, of being the universe's eyes and mind, fosters a profound sense of belonging. The feeling of cosmic loneliness, born from the initial shock of scale, dissolves when replaced by the understanding of intimate connection. We are not strangers in a hostile void. We are intrinsic parts of a single, vast, evolving entity. The awe inspired by the scale of IC 1101 is not just directed outward at a distant object, it reflects back inward, acknowledging that the same fundamental laws and primordial materials connect that colossal giant to our own small selves. There is a continuity, an unbroken chain of physical processes, linking the Big Bang to the beating of our own hearts. Now, let us introduce the moment of silence. Let the numbers fade, let the theories rest, let the comparisons cease. Simply be present with the reality revealed. Imagine floating in the quiet darkness between galaxies. Around you, in every direction, extends the cosmic web, filaments of light tracing unseen structures of dark matter, punctuated by clusters where galaxies swarm like luminous bees. Feel the immense distances, the billions of years light has traveled to bring faint images to your eyes. Sense the underlying expansion, the fabric of space-time itself stretching, carrying everything apart. Acknowledge the profound mystery of the dark components that dominate this reality, their nature hidden yet their influence undeniable. In this silence, feel the weight of deep time, the 13.8 billion years since the beginning. The slow, patient assembly of galaxies through countless mergers, the long life cycles of stars forging the elements, the gradual emergence of complexity on worlds like ours. Feel your own brief existence situated within that immense temporal flow. What arises in this silence? Perhaps a deep feeling of profound awe, not just intellectual appreciation, but a deeper, almost physical sense of wonder at the scale, the complexity, the inherent beauty, and the astonishing lawfulness of the cosmos. Awe at the fact that such a universe exists at all, and that we exist within it, capable of perceiving even a fraction of its grandeur. Awe at the delicate balance that allows our average galaxy to be a haven, that allows a planet like Earth to sustain life against the backdrop of cosmic indifference. This reflection allows us to hold the opposing truths simultaneously, our physical insignificance and our potential existential significance, our fleeting lifespan and our connection to deep time through the atoms we embody, our profound ignorance about the universe's ultimate nature, and our remarkable ability to comprehend its structure and history through reason and observation. The meaning, perhaps, lies not in finding a final answer or a definitive statement of human purpose within this vastness. The meaning may lie in the journey itself, in the relentless human drive to explore, to question, to push the boundaries of knowledge, even when confronted by the seemingly infinite. The comparison between the Milky Way and the giants is not just about cataloguing sizes. It is about calibrating our understanding, stretching our imagination, and ultimately, finding our own place within the spectrum of cosmic possibility. The reflection brings us back, finally, to the simple act of looking up at the night sky. That familiar canopy of stars, once the boundary of the known universe, is now understood as merely the inner tracery of our local galactic neighborhood. Beyond it, unseen by the naked eye but revealed by our instruments and our intellect, lie the trillions of other galaxies, the cosmic web, the echoes of the Big Bang. Yet, the feeling of wonder remains, perhaps even deepened by the knowledge of what lies hidden in the darkness. The silence of the night sky mirrors the silence of deep space, a quiet that holds both profound mystery and the potential for infinite discovery. To ponder the meaning is simply to stand in quiet awe of the fact that we can ponder at all. Small sparks of awareness adrift in the grand, silent, luminous city of the cosmos. Our long, quiet drift through the immense architecture of the cosmos draws now to its gentle conclusion. We embarked on a journey sparked by a simple comparison. Our home galaxy, the Milky Way, against the backdrop of the true giants that populate the universe. We began with the hook, the startling realization of our galaxy's profound averageness, a mediocrity that initially felt like a demotion but slowly revealed itself as perhaps a form of quiet grace. We grounded ourselves in the familiar setting of our spiral home, tracing its structure, acknowledging its beauty, and mapping our own small place within its vast rotating disk. We revisited the spark of discovery, Hubble's revolutionary proof of island universes lying millions of light-years away. The moment our perceived reality fractured and expanded beyond comprehension, we felt the first human response: shock, awe, and the immediate instinctive need to classify, to bring order to the bewildering diversity of galactic forms revealed in the deep sky. Yet, contradictions quickly arose, challenging simple narratives. The elegant tuning fork didn't match the story told by starlight. Theories of formation divided minds between monolithic collapse and hierarchical growth. And the universe revealed its ghostly majority, the pervasive, invisible presence of dark matter governing galactic motions. The investigation intensified, a relentless human pursuit employing ingenious tools to gather faint clues across cosmic time. The data accumulated, painting a quantitative picture of our average home against the colossal scale of giants like IC 1101, while simultaneously mapping the intricate structure of the cosmic web. This led us to the deeper mystery, the hidden truth that the visible universe is merely luminous foam on a dark ocean, its destiny shaped by unseen matter and the accelerating expansion driven by enigmatic dark energy. We experienced the turning point, that dual revelation of extragalactic scale and cosmic expansion that birthed modern cosmology. We traced the consequences rippling through science and the impact echoing through culture, technology, and our understanding of origins. We honored the human element, the dreamers and observers who navigated this path. We faced the stark opposition presented by the universe's remaining unknowns, and through it all, we reached an awakening, a new awareness valuing balance, seeing galaxies as ecosystems and embracing mystery. Finally, we arrived at the revelation, the unifying power of the Standard Cosmological Model, LCDM, explaining the observed diversity through hierarchical formation within an expanding universe dominated by dark components. We stepped back, in reflection, to ponder the profound meaning of our connection to this vast, ancient, and lawful cosmos, realizing our own substance is stardust, our consciousness perhaps the universe reflecting upon itself. Now, in this final chapter, we ask, what endures? What is the legacy of this immense journey of understanding? And how do we return, carrying this knowledge, back to the quiet wonder from which we began? The first part of the legacy is the ongoing scientific quest itself. The Standard Model, while remarkably successful, is not an endpoint but a sophisticated framework within which deeper questions now reside. The revelation wasn't a final answer, it was the clarification of the right questions to ask next. The legacy lives on in the relentless human drive to probe the remaining mysteries. What is dark matter? What is dark energy? How exactly did the first stars and galaxies ignite in the cosmic dawn? How precisely does feedback from black holes regulate galaxy growth? Are the observed tensions in cosmological parameters, like the Hubble constant, hints of new physics beyond the standard model? This legacy is embodied in the next generation of observatories, tools designed specifically to push against these frontiers. The James Webb Space Telescope, JWST, successor to Hubble, uses its immense mirror and infrared sensitivity to peer deeper into cosmic time than ever before, capturing light from the very first galaxies beginning to assemble in the infant universe. Upcoming ground-based giants like the Extremely Large Telescope, ELT, and the 30-meter telescope, TMTE, equipped with advanced adaptive optics, will provide unprecedented resolution, allowing detailed studies of star formation and dynamics in distant galaxies. Survey telescopes like the Vera C. Rubin Observatory will map the entire visible sky repeatedly, cataloging billions of galaxies, tracking supernovae, and charting the distribution of dark matter through weak gravitational lensing, providing crucial data to constrain the nature of dark energy and test cosmological models with unparalleled statistical power. The legacy is active. The investigation continues, fueled by the very mysteries the previous era uncovered. The legacy also endures in the profound shift in perspective that this cosmic knowledge imparts, a shift that transcends science and touches upon our collective human identity. We can never truly return to the pre-Copernican or pre-Hubble view of the cosmos. We carry, consciously or unconsciously, the awareness of existing within an immense, ancient, and evolving universe filled with trillions of galaxies. The legacy is this permanently altered context. It lives on in the enduring power of images like the blue marble, a constant reminder of our planet's fragility and interconnectedness, a perspective born directly from venturing far enough away to see home as a whole. It resonates in the scientific fact of our stellar origins, the knowledge that the atoms composing our bodies were forged in long-dead stars, connecting us intimately and materially to the galactic cycles of creation and destruction. This understanding fosters not alienation, but a deep sense of belonging, an echo of Carl Sagan's famous phrase, "We are a way for the cosmos to know itself." The legacy includes our refined understanding of our place within the Milky Way, not just physically in the Orion Spur, but perhaps conceptually within the galactic habitable zone, a region potentially favored for complex life due to its balance of chemical enrichment and environmental stability. This adds a layer of nuanced appreciation for the specific, perhaps fortunate, circumstances that allow our existence. It also includes the sobering awareness of our deep future, the inevitable merger with Andromeda, embedding our entire planetary and evolutionary story within a grander galactic narrative of collision and transformation. Now, how do we return from these vast conceptual landscapes back to the quiet wonder with which we began? The return is not a forgetting, but an integration. It is carrying the weight of this knowledge, the scales, the mysteries, the connections, back into the simple personal experience of looking up at the night sky. Imagine yourself, once more, under a dark, clear sky, far from the glare of city lights, that familiar faint band of light arches overhead the Milky Way. Before our journey, it might have seemed merely a beautiful, ethereal decoration. Now, imbued with the knowledge gained, it transforms. It is no longer just a band of light. It is the view from within our home city. You are looking edge-on through the flattened disk, seeing the combined glow of billions of distant, unresolved stars concentrated in the galactic plane. You recognize its structure now, the bulge hidden towards Sagittarius, the arms traced by faint dust lanes, your own location nestled quietly in a minor spur. It feels simultaneously vast and intimate. You see the individual stars scattered across the sky, no longer as mere points, but as suns, neighbors in our local region of the Orion Arm. You remember that most, if not all, likely host their own families of planets, hidden companions orbiting in the dark. Billions upon billions of potential worlds reside just within that visible band alone. The sky feels populated now, not empty. You look towards the faint smudge of Andromeda, if visible, and see not just a nebula, but a sister galaxy, slightly larger, bound to us by gravity, slowly approaching across millions of light years for an eventual, transformative embrace. You are witnessing, across deep time, the slow dance of cosmic structure formation. You contemplate the darkness between the stars, between the galaxies. It is no longer a void, but the realm of dark matter, the invisible scaffolding holding everything together. And you sense the underlying expansion of space-time itself, driven by the even more mysterious dark energy, carrying the most distant galaxies away from us, a silent, accelerating current in the cosmic ocean. The feeling is one of profound awe, but perhaps a different kind of awe than simple wonder. It is an informed awe, deepened by understanding, tempered by humility, and enriched by the recognition of connection. You feel your own physical link to this immensity, the stardust within you, the shared laws of physics, the participation in the same cosmic evolution. The comparison that launched our journey finds its resolution here, in this quiet return. The Milky Way is average, IC 1101 is a giant. But these labels now feel less like rankings and more like descriptions of different paths taken within the same grand, universal process of hierarchical growth. Our galaxy's averageness is not a failing, it is the condition that likely allowed our own awareness to bloom. The existence of giants does not diminish us. It expands our understanding of the universe's potential for building structure. The legacy endures in the questions that remain, fueling future exploration. The return culminates in a sense of peaceful belonging within this vast, dynamic, beautiful, and still profoundly mysterious universe. We are small, yes. Our time is fleeting, yes. But we are connected. We are aware. We are home. Let your thoughts settle now, like dust motes drifting in a quiet sunbeam. Feel the gentle pull of Earth's gravity, a local echo of the force that binds galaxies across billions of light years. Feel the warmth, perhaps, from our average, life-giving star. Listen to the silence, mirroring the silence between the stars. The Milky Way continues its slow rotation overhead. Light from distant galaxies continues its long journey towards us. The universe expands, evolves, creates, and dissolves according to its own deep rhythms. And you, here, now, are a part of that rhythm, not separate, not observing from outside, but intrinsically woven into the fabric of it all. Small, yes. Temporary, yes. But present, aware, connected. And perhaps, in that quiet realization, lies the truest, most enduring comparison of all.